Hi, and welcome to Section 9, where we take a look at motion analysis and object tracking. So in this section, we take a look at some of the key motion analysis and object tracking methods. We first go a bit back to basics and look at filtering by color. We then look at some simple background subtraction techniques, and then we explore some object tracking algorithms such as mean shift and cam shift. We then look at optical flow, which is a technique used to pick up the direction of movement in a video stream. And then finally, we implement a simple ball tracking project, so it's going to be quite fun. So starting off with color filtering. So why exactly is color filtering part of our motion analysis and object tracking section? Well, I've placed it here because it's actually a very useful technique when doing object tracking, because if you know the color of the object being tracked, we can easily separate it from the rest of the scene, as you will see very shortly. So some of these images here may look very familiar, and that's because they were part of the HSV color space section, and HSV is actually what enables us to do color filtering so easily. And why exactly is that? It's because colors are stored as hues, which are represented in the cylindrical representation here. And as you can see, it makes filtering by color quite easy here. So now we can easily pick out a range. So let's say we're looking at the color green. You can easily see that's 45 to 75, and if we wanted to be slightly more tolerant of shades of green, we can actually go up to 80 and maybe start at even 30 here. So by setting our upper bound and lower bound to say 30, 35 or 45 to 75, we can capture all the green segments of an image. And you may be wondering, do we use saturation and value when doing color filtering? And the answer is yes, we do. You can see here that if we were to filter by saturation, you can actually get different shades of the yellow or green perhaps by looking at saturation range. So typically, filtering at a range between 0 and 60 on saturation gives you the pale or whitish colors. And similarly for value, which is also called brightness, which, well, I should say also is brightness, if you were to look at the brightness or value scale here, you'd see the lower ranges of that value give you the darker colors as well. So always just keep that in mind when you're creating your color filters. Hue is the most important thing by far, but it isn't the only thing. So now let's implement our first color filter in code right now. Okay, so let's go ahead and open our code. That's Lecture 9.1. Okay, so here we have a relatively short piece of code, and it's actually pretty simple to explain. So I'm gonna just go ahead and run this code first, and you can see it in action. Okay, so here we have three windows. This is me in the original image here, and this window here is our mask. So you'll quickly see what our mask is. So let me hold the object up that we're filtering. You can see it's a purple calculator here, and if you notice, the mask is just like a binary image with white and black colors. And if you remember correctly from masking images, if we do a bitwise AND mask, so let's assume we do a mask with this window here and the original image here, which is myself holding this calculator. And what happens, any image here that's non-zero will actually be displayed here through when we apply our mask itself, or our bitwise operation, I should say. So that's how we create our color filter right here. So here we have this pretty cool filter, as you can see, and it's very good at picking up only the purple colors, and there's nothing else being displayed. It looks like the calculator is floating in midair. Ooh, nice. Okay, so let me quickly step through this code for you guys. So aside from our webcam initialization and our standard imports, you can see we're setting lower and upper boundaries to define our color purple. And this basically goes back to our HSV color filtering here. So this is the range of purple here. Let me just bring up the image for you guys. As you can see, purple color lies between a spectrum, say 125 or 120, well, sorry, 125 to roughly 175 or 170. So I would have used 125 and 175 here. And you may notice I'm also setting the full range of values for saturation and value here as well. You don't necessarily need to set this range so wide, especially if you're trying to get an object out of a cluttered image. However, this worked well with my purple calculator, but you can experiment with these values on your own. So let's move on to how we actually implement this color filter. So as you can see here, we're reading the images from our webcam, standard procedure again, and then converting it to an HSV image, which you would have seen in our first section or second section, I believe. And then we use the CV2 inRange function. So I may not have mentioned this function before, but basically what this inRange function does, it takes an HSV image here and basically filters the values from this HSV image array between lower blue and upper blue that we defined up here. So this creates our mask, and let me just bring up the mask image again. The mask was the black and white binarized image here. That's what it created. So once we have our mask, we can use our CV2 bitwise AND operation on our original frame image. That's the image with me with no filters, nothing applied to it, and our mask here. So we just set it mask equal to mask. That takes this image here, and this is the resultant image, which we then display here. So we were displaying those 3 windows as you just saw, and pressing enter key to exit, and that's basically all there is to this code. So it's pretty simple, but it's surprisingly useful though. So now let's move on to background subtraction. Okay, so let's talk a bit about background subtraction. Background subtraction is actually a very useful computer vision technique, and it's used to separate foregrounds from backgrounds in video streams. So what these algorithms do, they essentially learn from the video frame what's the background and what's the foreground, and they do this by basically detecting movement in a scene. So if a camera is looking at a stationary park or roadway for this instance here, all the movements of people or cars, etc., are deemed foreground. So whatever is not moving in the scene is actually learnt as the background. So that's essentially how it works, and then you can just apply masks to actually produce images like these. So now OpenCV actually comes built in with 3 background subtraction algorithms. I'm not going to get into the technical details of them here, but these are the 3 of them are listed here. And basically, background subtractor emoji is this image here. You can see it's pretty cool. And actually what's cool about the second version here, it actually can find shadows. So you can actually see the shadows of people or objects that are moving in the scene, which is pretty cool. And the geometric multigrid method here, this basically combines statistical background image estimation using a Bayesian method to predict this. Okay, so now let's move into the code and implement all 3 methods that we've just discussed. Okay, so let's go ahead and load our code for lecture 9.2, background subtraction. So here we have our code for those 3 background subtraction methods, and it's actually not a lot of code here, and it's not very difficult to explain. So quickly, what's going on here? We're loading our video stream here to Walking AVI. Then we're initializing our background subtractor by calling CV2 background subtractor MOG. And then to apply this, it would be basically access the .apply method here, and basically send our video stream frame right to it here. And this foreground mask is basically what you'll be seeing here. That's our background extracted or removed from our image. I hope you remember what this image looked like. There was a walkway here, and there was some grass here and a building here. So can we do this for our webcam? And in fact we can. So let's run this and you'll see me briefly here. However, what you're seeing me here is just me moving around. So if I stay perfectly still, I should say, you will eventually, I can't stay that still, but if I can, you will eventually see me merge into the background. I'm guessing because I'm talking too much, but you get the idea. And let's look at background subtractor MOG2, the improved Gaussian mixture model for background subtraction. And you can see it's pretty cool, and what we can see is that it's not as effective as removing the background. However, we can see shades of gray here that indicate shadows, so this is actually pretty cool, and it could be useful for certain applications as well. Okay, so we just saw this crash there, so that actually happens sometimes in OpenCV and Python when using these modules. They're not fully tested yet, so if you want to run this in a commercial application, sometimes you should be using the C++ version, so you can actually look at the code in a deeper level and maybe figure out what's causing these crashes. So now let's look at background subtractor MOG2. Let's keep this here for a webcam. This shouldn't crash, should be fine. Yeah, here we go. So let me hold perfectly still again. Yeah, I'm not that good at this apparently, but you get the idea as well. So what about foreground subtraction? Now, and this uses a different method to remove foregrounds from the image. It uses a method we call accumulated weight. So what accumulated weight does, it looks at movement in the image and basically accumulates weight for things that aren't moving. So that's essentially how it keeps the background in the image. And we then actually have to convert it to an absolute scale here, just so we can display it using our imshow function. So I'm going to show this to you quickly. You'll see two windows here. So this is me on the left here on the normal webcam stream, and as you can see, as I move around this image, I'm actually removing myself from the image here. So you actually get to see my bed frame in the back, which is totally not in view most times. So this is pretty cool. So you can imagine a cool application for this would be through a webcam or a city view cam, and you could technically remove people and traffic and cars from a view from an image just by having a long enough recording. So there's something I should have said at the beginning of this exercise, but I'll mention it to you now. These background subtraction methods here, they're only available in OpenCV 2.13. They have been left out of OpenCV 3.0 go forward, unfortunately. However, you can add them in, and I'll put some documentation at the end of this course on how we do that. Basically, it's just you have to compile it from the GitHub directory and add it to your OpenCV install. So it's not totally easy, but it's doable. So if you do have OpenCV 3.0, you can use background subtraction by KNN, and I left some code for you guys here. So I'm going to just quickly switch my OpenCV to OpenCV 3.0, and I do so by having both installed and just changing our CV2 file here. So actually it's quite easy to do for me. Okay, so I've just made my CV2 file the CV2 file for OpenCV 3.0. That's a larger file here. So this is the previous OpenCV 2.413 file here. So whenever I have to swap it back, I'll just put in brackets here, this is 3, and remove the brackets 2 here, and that's basically how I swap them. It's quite easy. So for those guys who have OpenCV 3.0 or 3.1 installed, you can run this code simply by doing this here. Actually, you have to refresh our browser, or IPython kernel I should say. There we go. So now when we reload, when we import CV2 this time, it's importing OpenCV 3.0. And yeah, there we go. So this is KNN background subtraction technique. Again, you can see it actually does pick up shadows in gray as well. And if I hold perfectly still, let's bring this up again. Yeah, I do disappear into the background except my mouth. And when I blink or move my eyes, it's picking it up quite good. So this is pretty cool. So for those of you using OpenCV 3.1 or 3.0, don't feel left out. You can actually implement your background subtraction right here. Okay, so let's first talk about mean shift. Now, mean shift is the first object tracking algorithm that we're going to look at in OpenCV, and the theory isn't too difficult for us to understand, so I'm going to explain it quickly with these three pictures here. So imagine we have an image where there are a high density of points here, and I'll show you how that density arises when we look at the code later on. So imagine we initialize our tracker or window at this point here, this red point here. However, let's take an average locations of all the blue points here. You'd actually figure out that the average location of a blue point actually lies where this triangle is here. So then we shift our window in the second step here to have this yellow triangle be our center, our new center for the window. However, again, you can see that the ratio of blue balls in the image here changes, and it's actually skewed much more this way. So then that's the center of the new points in that circle, and then we continuously shift this up. So that's basically or essentially how mean shift tracks objects here. So I'm going to take a look at our code. Let me just bring it up. And the code for this example is lecture 9.3. So let's just open this here. Okay, so unfortunately, mean shift is not available in OpenCV 2.413. It's only available in 3.0 plus. So I've just swapped my packages here. You can feel free to do the same if you wish, if you have both installed. If not, feel free to skip this section. Okay, so here we have our mean shift code. So it's a little bit lengthy, however it's not too difficult again to implement and understand. So let me just run this quickly and we can see how does it work. So right now that blue triangle is where it's initialized, and I've applied a purple filter. So as soon as I put our purple filter in this window, it should start tracking this object. So let's see if it works. And yes, it does. So it's actually working quite well. So you can see our box basically tracks this purple object throughout the scene quite nicely. So let's quickly step through this code so you guys can get an idea of how we implement and use mean shift object tracking. So we first initialize our webcam. That's pretty standard. However, we're not going straight into the webcam loop here. We're actually doing a lot of initializations here. And the reason we do that is because mean shift has to be set up basically so that we have our default image, we have our default locations and initialization values. So that's what's going on here. So first we set up our default location of the window, and you can set this to anything you wish. And we're capturing that frame, converting that frame to an HSV image, creating the mask using in-range function here. This is the purple filters we did in the first subsection of this section. And then here's something interesting here. We're calculating a histogram here for that region of interest here. And also we're normalizing that histogram data, and then we're applying this set of data here. And this is a criteria for mean shift itself. And what it says is basically if the centroid hasn't moved in 10 iterations, hasn't moved 1 pixel, then it basically just stays constant in that space. So all this is a bit tricky, and you don't need to understand it fully yet. You just need to basically implement it and maybe interfere or play with the color filters here and the initial start position. So here's where we actually implement our mean shift function now. So once we get our webcam image, we're converting it to HSV. Once the webcam image has been successfully read, that's what this ret is about, in case you forgot. Now this function here is a bit tricky, and I don't expect you to understand, so I'm not going to explain it in too much detail unless you're very curious about it. You can go read up on it on your own. But what it does, it basically calculates the histogram back projection. So basically it's the probability of a pixel's value. And the reason we do this is because this is how mean shift actually, and what mean shift uses to track the image itself. So, and then we draw the triangle, which is our tracking window as well, that was established up here. And that's basically all there is to it, essentially. So I've put some notes here on what CV2 calc histogram does and calc back project. So you can probably just take a quick read and go research it on your own if you're curious. So let's just run this again, see how it works. Yeah, works pretty good. Okay, so now let's take a look at camshift. So let's talk about camshift. Camshift is another object tracking algorithm, and it's very similar to mean shift. However, you may have noticed in mean shift, one of the weaknesses was our window size was fixed. Remember we defined those dimensions early on in the code? And obviously that is going to be problematic, because if you think about it, if there's a person moving in depth in the image, moving away from our camera, he is going to get smaller and smaller. And obviously our window is probably not going to adjust if he moves up as well into the frame. So that's the genesis of camshift. That's why it was created. So camshift actually has this continuously adaptive window, and that's why it's called continuously adaptive mean shift. And basically what it does, it applies mean shift until it converges, then it calculates the size of the window and then calculates the orientation of the window. Let's correct that there. Okay, good. So let's move on into the code and see camshift in action. Alright, so let's open our code. That's lection 9.4, camshift object tracking. And as you can see, this code, at least the beginning of this code, is actually pretty much identical to our mean shift tracking code. And the only difference here is that actually we're using camshift now. So we're doing pretty much everything exactly the same, except this using the CV2 camshift function. So let's go ahead and run this code. Just a reminder, we have to initialize a lot of stuff here, like the tracking window position and getting our first frame and calculating some stuff here. So let's go ahead and run this code. And before we do that, another key difference here is that because camshift has an adaptive window, Camshift actually returns a tracking window set of points here. So even though we've initialized our default tracking window size and location here, we do actually take up or update the window specs here. So then once it returns these specs here, we actually use polylines now to represent our adaptive box, and that's drawn on the image here, and that's how we do it. So let's see this in action. Just one thing, so unfortunately for OpenCV 2.413 and previous users, Camshift is also not available in that OpenCV version. You're going to need to upgrade to OpenCV 3.0 Plus to have access to Camshift. So anyway, let's run our code and see how well our our Camshift object tracking works. Alright, let's move this into view. Come on. Oh, there we go. Okay, so it's tracking our object. It's not too well, it's picking up other stuff in the image as well. But as you can see, the adaptive window is adapted perfectly to the shape of this object. So that's pretty cool. Okay, so that concludes our brief overview and introduction to Camshift. There's something else I want to mention. Let's go back to the notes, and that's basically how and when do we decide to use MeanShift or Camshift. So pretty much whenever you know the object size is going to be constant in your webcam view or your camera view, then MeanShift would probably be the best bet to use. However, if that object, like let's say your camera is facing a hallway and people are going to be moving away from the camera, so they're going to be getting smaller and smaller, you're going to want to use Camshift instead, mainly because of the adaptive window which you just saw. So there's another thing you should be aware of when using Camshift and MeanShift is that when you initialize the starting location, sometimes you can get stuck in a local minima. And what a local minima is pretty much just consider it being a region in an image where if you start the window in that specific region, it's never going to be able to get out of that region. That's basically what a local minima is. So you may want to randomize the location, the start position sometimes. Okay, so let's talk about optical flow. Optical flow is a very useful computer vision technique that is used to show the pattern of apparent motion of objects in an image, and it does this by looking at consecutive frames of that image. So basically what it does, it shows the distribution of apparent velocities of objects in an image. And this is a good example of it here. So imagine we're watching a video of a ball moving in this direction. Using optical flow, we'll be able to pick out the direction, or basically show the direction of movement as it moves across the frame. So there's some things to note about optical flow. Sometimes due to the camera perspective, objects that are closer to the camera itself are going to show much more or much faster apparent movement, and things that are far away are going to show much less movement. And one of the assumptions of optical flow is that objects maintain consistent intensity, which means that the neighboring pixels exhibit similar motion. That's how we actually look and track the objects in optical flow. So fortunately for us, OpenCV includes two very good optical flow algorithms. The first is the Lucas-Canade method, which is really good for tracking corner-like features in images. So you can imagine it being very useful in tracking a car while using a drone from this top-down perspective. And you can read more about the Lucas-Canade method at these two links here. They're quite informative. So moving on to the second method, which is dense optical flow. Now dense optical flow is definitely slower. And that's because unlike the Lucas-Canade method that was only looking at corner-like features, which is a sparse data set, dense optical flow computes for all points in a frame. So what's cool about dense optical flow though is that colors are used to reflect movement, with hue being used to indicate direction. So you can actually, this is an example of dense optical flow. So the colors actually indicate the direction of the people or the objects that are moving in this image, and the intensity or brightness of the image will indicate speed. So that's pretty cool. So now let's look at using these optical flow algorithms in our code. Okay, so let's go ahead and open the code for lecture 9.5 optical flow. And I'll quickly point out that again this only works in OpenCV 3.1. So unfortunately for users of OpenCV 2.4, you're going to have to upgrade to actually implement these. Okay, so let's go ahead and run this code and see if we can visualize our optical flow using the Lucas-Canade method. Okay, so here we are, and as we can see, it's leaving trails for people tracking here, so that's pretty cool. You'll see some people come right here, yeah. So all those trails are well implemented, so let's go ahead and close that. And let's actually implement the dense optical flow. So let's go ahead and run this. And here we are. So remember, color indicates the direction of the movement and the intensity indicates how fast the movement was. So you can see sometimes there are some very bright movements occasionally. That's probably fast movements either between swinging arms or legs as well, because this is the same video as before. And as you can see, the processing time or the frame rate has slowed down considerably, and that's because dense optical flow is computing it for all pixels in the image, which is why it's quite slow. So let's go ahead and stop this. Okay, so let me quickly run through the code so you guys can have an idea of what's going on here. I'm not going into any heavy detail, however I'm running through every line at a high level so you guys can understand what's going on. So firstly, we're establishing or initializing our video cam, or video stream I should say, and then we're defining the parameters for the Shai-Tomasi corner detection that's used in the Lucas-Kanade algorithm or optical flow algorithm here. That's later on in the code. So let's start back here. So we define the parameters for corner detection, and then we define the Lucas-Kanade parameters itself. Now it's a bit lengthy to define and explain what these parameters are here, so I'm not going to do that now. However, if you do desire it, I can put up a second video on it later on. But for now, we'll skip that. And what we're doing here in this line is defining a random set of colors, which is what we're going to use for the different trails in our image. And what we're doing here is establishing the corners, initial corners from the first frame that's captured from our video stream. And back to this line here, so yeah, we're kind of converting it to a gray image as well. And then we're also finding the initial corner locations using good features to track. So you may have remembered that algorithm from our corner detection section. And then we're creating an empty mask for this image here. And then once the loop has started, so once we start a loop through our frames in the video, that's where we actually use CV2's optical flow here, and using the Lucas-Kanade parameters we defined here. So this also takes into consideration the previous gray image, our current image, the previous corners, and an argument for none, which we don't use here. And and just moving on quickly, so we're storing the new and old corners that this function pulls here. As you can see, new corners here, and old corners were the previous corners from the loop itself. And then we're just drawing the tracks. So we're drawing the tracks using our corners that we got from here. And then we're just adding a frame to our mask, and then we're just displaying this image. So that's pretty much at a high level what's going on in this Lucas-Kanade implementation of optical flow. You can see it one more time. You can see our trails, and that's pretty cool. So now let's move on to the dense optical flow. So dense optical flow is a little bit less code here. However, its implementation is somewhat similar as well, in that we do capture the first frame, but we don't have to define corners anymore, because this is actually looking at every pixel here. So this is what we call this function here now while we go through our loop that loops through the video file. And basically it's this calc optical flow fairback, or Farnbach I should say, because this is from Gunnar Farnbach's algorithm. He's a guy who actually did a research paper on dense optical flow. So I'm not going to go into too much detail here because it gets a bit mathematical right now. However, this is what actually produces the color and magnitude scaling of different directions and different speeds as well, using these parameters, using the output from this function here. Okay, so let's just run this one more time and you can see it. So again, this is pretty cool, and again I'll tell you that colors represent direction of movement and the brightness represents the speed of movement. Okay, so that's it for optical flow. I hope you found it useful. And if you've got any questions, again, please message me on Udemy and I can explain these things in more detail if there's a demand for it. Okay, so welcome to our 11th mini project, which is making a simple object tracker, just like this here. Alright, so let's get started by moving into the code. Okay, so let's go ahead and open the code for lecture 9.6, which is our object or ball tracker. Now I said object because I don't have a ball on me right now. I did have one when I initially created this code here, but however that was back in Trinidad and Tobago, and now I'm back in London and I actually don't have a ball with me. Sounds a bit strange, but we'll use something else instead. We're using actually a purple calculator, which you saw before. So let's quickly run this code and you can get an idea of how well our object tracker works. Alright, so this is our calculator. Let's get out of the frame. There we go, it's tracking pretty nice. Just has some odd initialization issues. Let's make it really small, away from the frame, and it's back in view now. So this is pretty cool. It's making an infinity sign. Alright. Okay, so this code is actually pretty basic, so I'll step through it quickly. Let's cancel this. And what's going on here is that first we're doing some color filtering. So you remember color filtering from earlier in this section? Well, we're filtering the color purple. Previously I had blue because I had a blue ball back in Trinidad. It's no longer with me anymore. And let's see what else is going on in this code. So we're initializing our webcam. We're creating an empty array of points, which is where we're storing the location of our object. And basically color filtering here, take note OpenCV3.x users, you're going to have to use this line here to find contours instead of this line, so just comment this out and remove this comment if you're using OpenCV3.x. And this is the initialization of the center of our array. Let's do the English spelling there. So what's happening now is that once we've detected contours in our already masked image, that's what this does here. So once our image mask has contours, which is what we're finding here, we're stepping into this code now. And what this code does, it basically looks at the biggest contours. That's what this line does here. So we're sorting by OpenCV area essentially and extracting the max value from this and getting the radius of that circle, the minimum enclosing circle. You remember we used bounding rectangle when looking at contours. So now this gives us our circle. So you saw how our circle was our tracker was adaptive. Let me just run this by you guys again quickly. So you can quickly see, just remove the noise, that the circle is adaptive. It grows as I get closer to the image. Now it's taking up half the screen. So it's pretty cool. So let's move on to how we create our trail. So our trail is created by logging the moments. If you remember correctly, moments were the centroid locations of contours itself. So we get our center location here, and center consists of two values here, and that's when we don't find any contours, we assign it back to the initial position. And what we set here is a threshold. So this radius threshold is basically the size of the object that's being tracked. If it's too small, or if it's like, well, under 25 pixels, we stop tracking it, and when it's over 25 pixels, that's when we display our circle over the image here. And here we log our trail, our center points, and this is how we actually plot our center points now. So we loop over the set of tracked points. Once our radius again is greater than 25, it's the same threshold here. And basically we just use CV line to actually plot these points now. So we're just going through this loop of points here, and keep running through. And here's some little notes I should mention here. Every time the frame has been out for, well, every time the object has been out of view for 10 consecutive frames, we reset our trail. This way we prevent our trail from becoming too big and exploding all over our screen. And then we just flip our image here so it's more mirror-like, so the movement for our object tracker is more natural. And that's pretty much it. That's all there is to this. There are some other adjustments you can obviously make. You can make trails disappear after a period of time, which would be a cool thing to do. You can make it correspond to speed as well, change colors of trails according to speed. There's many other things you can do, and if you want to change the color of the object you're setting, you can just change it here. And we can go back to our color wheel, or HSV color wheel, so you can decide what color you want to filter on here. So it's pretty easy and basic to use. And that's pretty much it. I hope you enjoyed our object tracking, or our supposedly ball tracking project. Thanks. Hi guys, and welcome to our 12th mini project, where you're going to perform some photo restoration using OpenCV. So what we'll be doing is we're taking a damaged photo of Abraham Lincoln here, and that's the image we'll be using, and we're going to implement some photo restoration techniques where we can remove these paper folds here and these vertical lines here, and we're going to be producing this cleaned up image over here. So let's take a look at how we do this. So before we dive into the code, I'll quickly explain what computational photography is, because photo restoration actually falls under one of the many computational photography algorithms. So firstly, computational photography refers to image processing techniques that seek to improve the quality of images taken by digital cameras and sensors. Now, pro photographers would typically spend thousands of dollars to buy better camera equipment, which offers superior sensors and lens systems to improve their quality. However, obviously that's very expensive and bulky. So image processing techniques have actually become so advanced that even today's smartphones, which have tiny cameras like the iPhone 7, can in fact offer image quality that's comparable to older model DSLRs. Of course, they don't have the flexibility and control offered by DSLRs. However, the image quality is remarkably good and pretty much good enough for most scenarios. So some examples of computational photography techniques include noise reduction, high dynamic range photos, image stabilization, panorama stitching, and what we're going to implement in our mini project today, which is inpainting. This can be used to remove small noises, strokes, and folds. Okay, so let's go ahead and open our code. That's lecture 10.3, which apparently has been sorted poorly by IPython Notebook's browser here. So let's bring it up. And here we have a relatively short code that does this project. So let's quickly run this code and get an idea what's going on. So the first image is here. So that's our damaged photo of Abe Lincoln. This here is our file that we created. It's a mask file, and I'll quickly show you how to create this. This is the threshold binary of that mask file, and this is when we dilate that mask, and this is the in-painted restored image. Okay, so you saw you had some image mask to create. However, how did we create that mask? Now let's bring this up quickly here. This image here is our original image. However, what I did, I went into Windows Paint and I basically drew some white lines over the spots we wanted to fix. So basically we need to do that, and you can easily just do it with Windows Paint or something similar on Mac or Ubuntu or Linux. So that's necessary, and what we do is actually we take this image now. Let's run our code one more time, and we grayscale it here, and then we apply a threshold, and the threshold is basically going to remove all our colors here except the white lines on our image. So that leaves us with this sort of dotted line image here because of our threshold settings we used. And then so we need to basically enlarge or thicken these lines and fill all their small gaps in. So that's what the dilated mask did. We dilated our image to get our mask, and then basically what we've done after that is just feed this masked image here and this original damaged photo here into our CV2 inpaint function, which you will see shortly. It's at the bottom here actually. It's probably out of your view though. And it produces this. So let's quickly go back to our code and you can see the steps we just discussed. So we load our and show original photo. Then we show the photo I created, the marked photo, which I'll quickly make it in Windows Paint to show you guys how I did it. And then we actually threshold that image here. And I set the threshold value at 254. That's an extremely high value to threshold, but we can do that because I knew I used white when painting in Windows Paint. I didn't want any color other than the white boundaries there. Because as you can see, Abraham Lincoln does have some white in the photo. If I were to set that boundary to say maybe 200 or 220, this image here, this spot here would come up in a mask, and that's not what we want. And after that I just apply some heavy dilation here. As you remember, dilation adds pixels to the boundaries of pixels, of the existing object pixels. So that's how we thicken our line on the thresholded mask here. And then this is the main function here, what it's doing. This is the CV2 inpaint function that takes our image, our mask, and some parameter settings, which I'll discuss shortly, and it produces our restored image. Okay, so let me quickly go over the parameters we use in the CV2.inpaint function. So there's two main parameters here aside from the input image and the mask that we created previously. So there's what they call inpaint radius, And what that radius is basically the radius of the circular neighborhood of each point to be inpainted that's actually considered and used by the algorithm. So what happens is that if you use smaller values, the images tend to look less blurred at those points where the mask is. However, you do sometimes see still noisy detail there. So if you really wanted to remove all the noise and scratches in an image, you would probably increase this radius slightly. However, be prepared to have it look a bit more blurry and a bit more pixelated at those points. So now let's get down to the input in paint methods that are available in OpenCV. So firstly, the Naivas-Stokes method, which was earlier or one of the first methods of inpainting, which was developed in 2001, is also used. However, the Telia method is actually superior. It seems to integrate more seamlessly and better into the image, so I'd recommend in most cases you use Telia. Okay, so that's it for inpainting. I hope you enjoyed this mini project, and I hope you enjoyed most of the mini projects on this course. That's it for all our mini projects for now, until I add more bonus content. And if there's any demand for specific projects, please let me know, and I'll be happy to implement them and share them with you. So congratulations on making it to the end of the course. I really hope you enjoyed it. I honestly did try my best to teach you the most relevant and useful areas of computer vision to give you the best foundation possible. So there are a few things I want to address in concluding this course, and that is, where exactly do you go from here? What can you do and how can you do it? And secondly, I just want to bring you the latest areas of research in computer vision and share some very cool startup ideas as well. Additionally, I would just like to teach you and give you a heads up on how to get started in mobile computer vision application building. So let's do a quick recap on what you know now. You definitely would have become familiar with Python and NumPy, which is an excellent skill set to have. And regarding the main part of the course, which is computer vision, you would have seen a lot of image manipulations and segmentation. You would have covered quite a bit of object recognition methods. You would have gotten a good start in machine learning in computer vision, and done some very cool stuff with facial feature analysis and recognition. And lastly, we covered some motion analysis and object tracking, all of which gives you an excellent foundation in order to master computer vision. So if you truly want to become an expert, and I'm talking like a research level PhD expert, here's my advice on actually how to go about achieving that. Firstly, always try to implement your own project or projects. It's going to be so helpful and so educational, and the foundational knowledge I gave you here will give you a huge head start in actually implementing real-world projects. Secondly, definitely read and even try to implement those research papers I sprinkled throughout the course. I've actually compiled all of them, as well as some additional tutorials and information, in a document called Research Papers and URLs. It's in the attached course material, so make sure and check it out. And lastly, make sure and visit some of these computer vision sites or blogs. PyImageSearch, which is run by Adrian Rosebrock, is simply outstanding. He has so many useful tutorials, and if it wasn't for him, I honestly would have struggled implementing most of my computer vision projects. Secondly, Satya Malik, who runs learnopencv.com. This site is quite good. It's probably a bit more advanced than PyImageSearch, however it's excellent as well, and also has C++ tutorials as well if you want to look into that. AIShark.in has some good sites, it has some really nice projects, and he breaks it down quite nicely. And if you want to keep track of what's going on in OpenCV, I encourage you to just visit opencv.org's news category. It's actually quite good, and you get to see the latest updates and what's been added and fixed, etc. So definitely keep these things in mind if you really want to become an expert at computer vision. So in the current computer vision research area, things are moving surprisingly fast. Not a week goes by when you don't see a huge breakthrough from Google, Facebook or Microsoft in so many aspects of computer vision. And I honestly did have a lot more slides detailing all those key advancements in the field. However, I realized these things are changing so fast, and by the time this course goes up on Udemy and a month or two goes by, it's going to be heavily outdated. Instead, I'll tell you that the current sphere of computer vision is completely dominated by deep belief and convolutional neural networks. If you want to stay current with the latest developments in computer vision, you'll definitely need to get into deep belief and convolutional neural nets. Thankfully, I've put some of the best tutorials for these topics here, definitely check them out. Caffe and TensorFlow are neural net frameworks, and Stanford's CS231 class is exceptional. It's a computer vision neural net class. Definitely start with this first. And when you choose, or when you want to actually get more into the theory of deep learning, these links here are exceptional as well. So I told you I'd be sharing some startup ideas, and I'm coming through on that now. So here are 12 awesome startup ideas that, if you want, feel free to actually implement them. Just remember to give me at least 1% equity in your company. Just kidding, but that would be nice. So anyway, I'll just quickly share with you some of these ideas. So the first one I was thinking about was fall detection for elderly people. There is a lot of research in this area, and I think it would be quite a good product, especially in like nursing homes or even in elderly people who live alone. Just being able to figure out if they're in trouble before they even fall would be priceless information. Secondly, let's look at using drones or cameras on drones to find lost hikers. That would be a good application for computer vision. Or what about using these same drones to maybe count people in crowds, or even tailing like pickpockets or whatever? Let's look at number 4, which is using CCTV footage to create some sort of smart surveillance system, so you can detect when children are near like a pool or a balcony edge. That would be very useful for paranoid parents. And what about using drones again to actually monitor crops? You can check harvest levels, diseases, irrigation issues, anything like that. And what about in medical imaging? There's a huge computer vision sphere going on there. And what about identifying swimmers in the ocean who may have like a drowning person detection? That would be pretty cool. As well as finding counterfeit money. Or what about making a cool novelty viral app? Maybe one that you can take a picture of your chess or checkers board, and it actually gives you the next best move that you should be making against your opponent. That would be pretty sneaky, but also a very cool app. Secondly, what about taking a picture of any product and it actually brings up reviews on the prices of that item online? And I've actually seen people try this already, taking a picture of food on a plate and actually giving you the calories of that food and macros. That would be quite useful for especially people on a diet or keeping strict track of their diet. And a lot of work is actually being done in analyzing faces, but there's always room for more. There's so many cool things you can do with faces, and I actually showed you facial landmark detection, which is how a lot of these things do this stuff anyway. And if you want to see a lot more startup ideas, or just ideas for startups, check out Stanford's CS229 machine learning site. They've listed a lot of machine learning projects that students do there, and a lot of them are actually quite original and quite exciting stuff. So finally we come to the last slide in this course, at least for now, and that's basically discussing OpenCV in mobile apps or web apps. And I'll tell you a bit how to create those things. So firstly, if you're building a web app or a mobile app, you can do it 2 ways. You can create it as a RESTful API, and can use and since we're using Python, we can simply embed our OpenCV code into a Django or Flask bundle. And basically what that means is that you can actually send information or images to your API, and your API returns something back to you. So the pros of this is that it can be accessed on any mobile device or PC or Mac, basically anywhere that has an internet connection and a camera to take the picture. Obviously it's fine, it's going to work. But the problem with that though is that it requires an internet connection, so that may be an issue sometimes. Good thing though is that it can be updated remotely since it's cloud based, and we can offload all the powerful processing that needs to be done, so that's quite cool. However, we will need to pay for that hosting, so that's a downside. And you can do video using an API, at least not in any real-time sense. It's going to be too much bandwidth and too much issues as well, so videos are probably a no-no using APIs. So if you're doing a mobile app and you want to do video analysis, like maybe what Masquerade does or Snapchat with filters, then you definitely need to do native mobile OpenCV. And the R wrappers, OpenCV does come with like wrappers for iOS and Android, and I've listed the links here so you can get started on those as well. So the pro is that you definitely can do video-based real-time computer vision apps, and there's no need to pay for cloud storage as well. Everything is stored natively on the phone. However, because everything is being processed on the phone, you can't really do very heavy processing on the mobile phone. However, there are techniques like offloading to GPU and parallel processing, which can definitely speed up most apps. However, obviously that's very technical and that's what takes a lot of time. And it's definitely more difficult doing OpenCV in mobile apps than in Python. Python is definitely easiest and best way to get started into OpenCV. And mobile OpenCV is not as sophisticated. It doesn't have as much online communities and tutorials and support. So you should probably become pretty good with OpenCV and Python first before tackling iOS and Android applications. So that's it for the course, at least for now. I will obviously add more content as things come up. However, as it is, this is the main course, and I really hope you enjoyed it and got a lot out of it. If there's anything you want me to add or anything to stress on, it can be totally anything. It can be deep learning, augmented reality, 3D reconstruction. Those are 2 topics I haven't touched on in this course, and mainly because they're a bit challenging in OpenCV to do really cool real-world applications with them. However, if there's a need for it, I will definitely teach it in this course. So thank you a lot for purchasing this course, and it was a pleasure being your instructor. Alright, so welcome to chapter 3, where we set up our deep learning development machine. So now that you've gone through the intro, you're now ready to get started setting up your machine. So let's get to it. So now the first step in setting up our deep learning virtual machine is you need to download VirtualBox. VirtualBox is a software that allows us to actually start an entirely new operating system, whether it be Linux, Windows, or Mac OS, although it's not fully supported for Mac OS. But you can actually run an entire new operating system within VirtualBox. It's super cool. It's called virtualization, and it is super fast on new CPUs. They don't experience any slowdown really, and it is entirely useful for us to set up our deep learning machine, because deep learning software on Windows is not well supported. However, on Linux or Ubuntu, it is a very good environment for running our software. So what you do now is you download either the Windows or OS X versions according to what OS you're using. So I'm assuming it's going to be Windows, so I've already downloaded it here. So now what you do as well is you download from the link in the resources file, download your deep learning CV Ubuntu.ova file. This is your virtual machine that we're going to set up. So now that you have those 2 files here, we are ready to get started. So now we have to firstly install VirtualBox. Now I know this file is quite huge, it's 9 gigs, so you probably would have wanted to leave this overnight if you have a relatively slow broadband connection. However, if you have a fast connection, it should take about an hour. Either way, let's install VirtualBox. So you go to run, standard procedure. I'm not going to do the Mac install video because I don't have access to a Mac, but as soon as I do, I'll upload a video for you Mac users. However, it's a standard installation procedure, and all the settings are the same generally for Mac and Windows, so this should relate to you as well. So you leave all the defaults here as well. Just press next, next again. You can optionally you can do this if you want, it's fine. This is fine, press yes, install, and there we go. Okay, so we've finished the installation process, so now you can start your VirtualBox software, and I'll show you how to get everything set up. Alright, so here we are on our VirtualBox Manager software. So please ignore these 2 virtual machines I have up right now. Yours is going to be blank right now, since I assume it's the first time you're going to be using this. So go to File and Import Appliance, and now go to the directory where you downloaded your VirtualBox.ova file. Alright. So go to open and press next. Now I have it set to, for my virtual machine, to use 4 CPUs and use 8 gigs of RAM. That is basically, I have a quad core CPU, so I have 8 logical cores, and I have 16 gigs of RAM in my system. So you're going to want to put it to at least half of what your host system can support. So if you have a dual core, you can use 2 here, and if you have 8 gigs of RAM, you can use 4 gigs here. So we can make those adjustments and leave everything else the same. This is fine. And then go to import. And now this time is basically a lie. It's going to take maybe about 10-20 minutes. So I'm going to pause the video here And when it's done, we can start our virtual machine, and I'll show you how to use it. It's quite easy, and we'll download and set up our code, and that should be it. Okay, so that's it. We have just installed our virtual machine. So now this is the new one here. Because I already have it working here, it came up as _1. Yours is going to be this one. So either way, it's the same machine. So let's just start this one, the fresh one I just installed. It takes about maybe 30 seconds to boot up, at least on my system. This is all normal, by the way. It's a booting screen for Ubuntu. There we go. So we've loaded our OS. So this is pretty cool. So now you're actually running Ubuntu within Windows. And it's because it's using your virtualization features on your CPU, it's going to run pretty quick. You're not going to notice much of a slowdown. So what I want to do is two things I want to show you. First of all, your password for your virtual machine. Whenever you do sudo or any sort of like system settings where you change users and stuff, the password for this user is 11223344. It's going to be in the attached resources of your file, and I'm going to display it on screen as well, so you don't forget it. So let's just see something here. So what I want to show you is that we have this is our machine, this is our file structure here. So this is our home directory right now. We have a bunch of things installed here right now. Basically these things are a lot of your deep learning libraries, and I have some instructions as well. You don't need to use these right now, but what I want to show you is to basically set up your code and train models. Okay, so stay tuned. Okay, so what I'm going to need you to do is open Firefox. That's a web browser on Ubuntu by default. And what to do is when Firefox boots up, I want you to go to your Udemy account on udemy.com, and with the attached resources to this lesson, which is also the deep learning code library. Just wait for it to boot up here. I think my system has a lot of stuff running right now, but either way, let's just go to udemy.com. And there's a Black Friday sale going on right now. How nice. So what to do is basically log into your account, however you've done it before, whichever method you use, and download the resources for the course. That's the code and train model zip file. And download it, and it's going to save in your downloads folder right here. This is the same folder, and this is a file I want you to extract. So double click on this file. It's going to take a bit for 10 seconds or so to open. It's a big file, so that's reasonable. And this file here, I want you to extract it to your home directory here. So let's go ahead and do that. Let's just reduce this clutter in the background. And this takes about a minute, actually much less than a minute to extract. And when it's done, you will see all our code that we need for this course is in a convenient location. So let me just quit this. I'll close. Okay. And it's doing something, but that's fine. What I want to do is go to home, and now you see this directory here, Deep Learning CV, and this is also a shortcut to that same directory. And let's go back to it here. This is the contents of this directory. So let's sort it on list here. This is all the code and train models you're going to need for this course, and it's conveniently extracted now within your virtual machine. So now let's go back to our our terminal. So let's clear this. So what if we wanted to test our code? So what you do, you press source, type source, activate CV. That's our deep learning environment for computer vision, and it's instantly done. And now you type IPython notebook, and some magic happens. What this does is starts a local server that hosts your IPython notebook browser. So now, this is where we run all our Python code. And I'm just going to do a brief tutorial on it here. So now, just go to Deep Learning CV. Let's just go to chapter 4, getting started. And let's run our, let's run our live sketching. Because this loads much quicker and we don't need to download any files for this. So, to run this block of code, IPython notebooks are basically just blocks of code we can run. And all the variables, everything is stored inside of it. So you press Shift Enter or Control Enter. Shift Enter runs it here. This takes about maybe 5 seconds to import or less. And we print the version of OpenCV that we're using. It's 3.4. If you press Alt Enter, you get a new line below. So that's sometimes convenient, sometimes not. Shift Enter just runs it without producing this new cell here. And to delete it, just press Cut. So now let's run our sketch. Now before we do this, we're going to have to go to Devices, here, Webcams, and tick off our integrated webcam. And now let's press Shift Enter to run this block of code. There we go. So this is our browser, our live sketch. This is me chatting here. This is my microphone, the doors in the back. So this is pretty cool, isn't it? So let's close this. And that is it. So we have all our code here. Everything is pre-installed. All our Keras, TensorFlow, a bunch of supporting libraries. Dlib is installed. A lot of things are installed actually. It probably takes about an hour or even 3 hours sometimes to install everything. So that's it. You have your full virtual machine running here. Okay, so as I said in chapter 4.1, we're going to use an already trained, and you'll understand what training is later on. But you're going to use something that we actually create in this course in the next couple chapters to classify handwritten digits. So it's going to be pretty cool. So let's get started. Okay, so let's bring up our development environment, and that's source activate CV. And now let's bring up our IPython notebook. So let's type IPython notebook. And there we go. Mozilla should launch, and we should have basically our home folder information here. So let's go to Deep Learning, which is where all our projects, or 90% of our projects, are located. And let's go to chapter 4, which is our first chapter. As you can see, all the chapters are here. And let's open this one. And it should bring up this. This is called an IPython notebook. And I've left some simple notes here, some comments here. This one, I'm not going to actually teach much from this course here, from this code here, sorry. I'm just going to actually execute it, and we get to see what it does. So basically, before I begin, let me just briefly discuss the code. These are our imports here. We're importing OpenCV, NumPy, which is our array processing library, and Keras, which I'll teach you about later on. Keras is basically the framework, the deep learning framework we use to basically control and operate TensorFlow, which runs in the background, and that does all our deep learning stuff. So we're loading the MNIST dataset here, and that's how we're importing this from Keras here. Loading our model, and then this is a function we use to basically draw the prediction, what our model makes, over the actual digit. And you know what? Let's just actually run this and see how it works. So it's loading. This asterisk here means it's loading. Ah, there we go. So now we have basically what this does. It brings up a number from a test data set. Test data set is basically images that the the deep learning algorithm has not seen. And basically it tells you that it never saw this digit before in its life, but it tells you it's able to figure out that this is a 4. So now if you press enter, it goes through another image, and it basically does this up to 10 images here. You can go up to 50, 100, 1,000 if you want. Although I don't recommend going up to 1,000. This is a 2. Actually, this is pretty good. It's an 8. Good. 1, 1, 6, 8, 3, 5, 6. Perfect. So it appears this model that I trained here, called MNIST Simple CNN, is actually quite good at reading our models, our numbers, sorry. So can this work on real numbers now? What do I mean by real numbers? Well, let's find out. Let's run this. If I didn't mention it to you before, Enter and Shift on a keyboard together basically executes the code in the cell block. I should have mentioned that in the beginning, but now you know. Okay, so this is numbers that I actually wrote and took a picture with my phone. And basically what the code I've done here, it basically uses OpenCV to extract the digits here. And then it pre-processes it to basically make it look as similar as the training data for the MNIST dataset looked. And let's see. So basically what it did, it took out this one, and you previously saw how the MNIST dataset images were basically grayscale and white on black background. So it picked this out, extracted it here. This is a contour we drew over it here, and immediately it classifies this as 1, and it puts a 1 here. So that's pretty good. Let's see if it gets a tree correct. Bingo, got the tree exactly right. Got the 5 exactly right. 4, 0, perfect. So all of this here is my OpenCV code, and if you want to understand how this code works, I'm not going to explain it to you thoroughly here, but this should be fine. But I'm actually going to tell you that if you do want to learn this, look at my OpenCV tutorial. It'll teach you all of these things, what Gaussian blur, canny edges, contours, how these things work, how to use functions, and you're sorting your contours here, how to actually sort contours and bring them up and extract them, and then feed them to a classifier, which is what we're doing here, the same classifier we used up here. So we're pretty good. You just actually use a handwritten digit classifier that I built, and you're going to build it soon. Actually, perhaps you can build it right now. This is a code where I'm not going to go through in detail, as I said, but this is a code that actually allows you to train that classifier. It is not as complicated as it looks here. If you're unfamiliar with it, I expect you to be a little confused. What the hell is batch size? What are epochs? What is going on here? Blah, blah, blah. But don't worry, all of these things will be made very simple soon. And basically you'll understand what these lines mean here, what this means here. This is actually our accuracy of our model, 99.07, which is pretty good. Not top of the line state of the art, but pretty good. And stay tuned, you're going to learn how to do this in the upcoming chapters. Okay, so in section 4.2, we're actually going to use probably a little more complicated image classifier, one that classifies 10 different objects, and you'll see those objects very soon. So let's get started. Okay, so now let's open section 4.2, which I called image classifier CIFAR10. Probably could have come up with a cooler name. Okay, so I mentioned we're going to classify 10 different objects. What this model CIFAR10 is, it's a pretty large model dataset that has thousands of pictures of airplanes, automobiles, birds, cats, deers, dogs, frogs, horses, ships, and trucks. Not entirely sure how they chose these categories of images, but maybe it was just for purely research purposes to build image classifiers to detect how well it can pick out these images from data it receives, from images that it receives. So again, this is a model I trained, and I don't believe this model is actually super accurate, but let's run this model and let's find out. There's an error here before, but probably maybe I fixed it. Let's find out. Ah, it didn't happen again. Good. So now, it says this is a ship, and this is clearly a car, so we immediately know this model isn't great. But it got the deer right. At least I think this is a deer. Got the truck right. Truck again. Got the frog right. Looks like a frog, but it was a ship. It's called it. Automobile. Bird. Definitely not a truck. It looks like a cat. This is a truck. So let's run it one more time. Remember to run, you press Shift and Enter together, and it usually pops up on a window here. In Windows, it pops up on top of the screen, which is quite nice. On Ubuntu, it comes up in the background, so you kind of have to look for it there. But it kind of does a little shimmy shake thing here, so if you're paying attention, you should have seen it. So it got the ship right. It's not a truck, it's a frog. It's not a dog, it's a cat. It's not a ship, it's a bird. This is a dog. This is a deer. This is an airplane. This is car or truck. I'm not sure entirely what they would have labeled it as. Truck for sure, truck for sure. So As I said, this model I trained here isn't a very good model. I think the accuracy I got on this one was 60 or 70%. I actually could have got a lot higher if I left it for longer. Probably didn't want to. But it gives you a good idea of limitations of training a model for a short period of time, which was this, and this was called so far simple. I think I used a very simple CNN for this one. And later on in the course, you're actually going to use far more complicated models that we're going to train for a longer time to get even higher accuracies on these. Hi, and welcome to chapter 6, which is probably the most important chapter, or maybe second most important chapter in this course, and that's basically a very good and detailed explanation about neural networks. So let's see what this chapter comprises of. So the neural networks explained chapter, firstly, I give a machine learning overview, because deep learning and neural networks are essentially a machine learning algorithm, and perhaps one of the best ones ever. Next, I go into forward propagation, which you'll learn about shortly, activation functions, training part 1, which is the loss function, then training part 2, which talks about backpropagation and gradient descent. Then I actually go through backpropagation in detail. I actually work through an example with the mathematics, mainly because backpropagation is critical for training neural networks and convolutional neural networks. And then I go into regularization, overfitting, generalization, and understanding test data sets. Then I talk about some terms you'll probably see a lot in future in this course, which are epochs, iterations, and batch sizes. Then I talk about how to measure performance and how to analyze your performance with the confusion matrix. And basically then I go do a recap of the entire chapter, mainly because there's so many moving bits in it. And I talk about the best practices involved in training neural nets. So stay tuned, 6.1 is coming up, which is a machine learning overview. Hi, and welcome to chapter 6.1, which is basically a machine learning crash course overview. Alright, so let's get started into this. So what is machine learning? Now, machine learning has been synonymous to artificial intelligence because basically it's a field of study that basically studies how algorithms or software actually learns from data. So basically, as I said, it's a subfield or field in artificial intelligence that uses statistical techniques to give computers the ability to learn from data without being explicitly programmed. And explicitly means like, if this is that and that is that, basically a hard lookup table of criteria. Machine learning does not do that. It actually learns from the data. It learns its own model of how it should be answered. And basically over the last 5 to 10 years, maybe even 15 years or so, machine learning has exploded. There are basically a number of masters and BSc programs all over the world have specializations in machine learning nowadays. And this has mainly been brought upon because processing power, and also from GPUs, has basically caught up to the processive intensity required for machine learning. So there are 4 types of machine learning, with neural networks being basically one type belonging to a subtype belonging to one type of these 4. These 4 are basically supervised, unsupervised, self-supervised, and reinforcement learning. And I'm going to talk a little bit about each one. So firstly, supervised learning. Now, supervised learning is by far the most popular form of AI and ML used today, ML being machine learning. Basically because it's relatively easy compared to other things to implement. All we need is a labeled data set, and we feed this labeled data set into a machine learning model or algorithm, and it develops a model to fit this data to some outputs. So basically, it's like an example here is, let's say we have 10,000 emails that are labeled spam, 10,000 that are not spam, and we give this to a model. Basically, we give the text and basically subjects and from the sender of the email, and now the machine learning algorithm is now going to figure out what is spam based on that. So we have the input data being an email, our model that we just trained, and it outputs whether it's spam or not. So that, in a nutshell, is supervised learning. And here are some examples of supervised learning in computer vision. Basically, it's used heavily in image classification, even object detection and segmentation. Basically, all of these involve feeding some labeled data into our deep learning model, and training it and getting a model that is accurate enough to take unseen data and classify them correctly. So what about unsupervised learning? Now, unsupervised learning is concerned with finding interesting clusters in the input data, and it does so without any help of data labeling. So you just feed some data into it, and the unsupervised learning algorithm basically finds some interesting patterns and clusters in the information. It is actually very important in data analytics when you're trying to understand vast amounts of data. Basically when you have huge data sets with huge number of columns and rows and different information, using unsupervised learning can help you understand very quickly what is important in your data. This is a basic example of it here. So go back to it. So now imagine we have basically meats or food items here, and we give it, let's assume this is pictures here, okay? And we give it to an unsupervised machine learning algorithm, and it's going to actually pick out cluster 1 and cluster 2, and I'm willing to bet cluster 1 is going to be the first tree, and cluster 2 is going to be desserts. So meats versus desserts. That is the interesting pattern our unsupervised machine learning algorithms help us pick out. So what about self-supervised learning? Now, self-supervised learning is the same concept as supervised learning. However, the data is not labeled by humans, which is pretty interesting. So how are these labels generated? Basically, it's done using heuristic algorithms, for example, autoencoders. And a good example of that is basically trying to predict the next frame in a video given the previous frames. That's a very good example of self-supervised learning. We're not going to deal with any self-supervised or unsupervised learning in this course, but it's good to know if you want to have an overview of machine learning, what they're about. And lastly, we have reinforcement learning. Now, reinforcement learning is potentially very interesting, but however, it's still in its infancy, and it's still a bit tricky to actually do. I actually did a couple classes on this in my university in Edinburgh, and it wasn't that fun. It was actually very challenging, but once I got it working, it was actually quite fun, quite cool. So the concept is pretty simple. However, it's not that simple to implement, but we basically teach an algorithm something by giving it bad examples or penalties against something. So sort of like learning to play games is a very good example of reinforcement learning. You're basically trying different things and getting punished or dying or losing points for something until you come up with a strategy where you're basically minimizing your loss. That is what reinforcement learning technically is. So in machine learning, in supervised machine learning, there's a basic general process which you follow in using every algorithm, whether it be deep learning, convolutional neural nets, SVMs, blah, blah, blah. They all follow this pattern. So in step 1, you obtain a labeled dataset. Step 2, you split this dataset, this is very important, into a training portion and a validation or test portion. Now there is technically a little difference between the validation and test portion. However, for all intents and purposes, which is a bad phrase I shouldn't be using, but whatever, basically the validation and test portion is basically the unseen data. Your model never sees this data, your model only sees the training data, and we test performance on the validation or test portion, test data sets. So in step 3, we take this training data set that we split from the original, and we feed it to a model. So a model takes this data and its inputs or labels, and basically learns, tries to figure out patterns. How do I predict this? How do I know what this is? And after some time, it develops a fully trained model. And in step 4, basically we run this model on our test or validation data set to see how effective it is. So here's some machine learning terminology that you're probably going to hear in this course and in the AI world. Basically, target data always refers to the ground truth labels. Technically, in programming languages, you'll see that referred to as the Y, or in mathematics, the Y labels, X being the training data set. Sorry about that. And prediction basically being what our model predicted from some input data. Classes will be basically the categories of your data. So if we were talking about the handwritten digit MNIST dataset, there were 10 classes there. That would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Regression refers to when you're in classes, we're outputting basically this image belongs to this class. Regression, now we're outputting basically a continuous value digit or number. So let's say we're taking some inputs and trying to predict someone's height or weight. That would be a regression model. And as I mentioned before, validation/tests, yes, they can be different, but generally refers to unseen data that we test our trained model on. Okay, so finally let's get down to it, and let's get into neural networks. And I assure you, this is probably the best explanation you'll ever see on neural networks online. So let's get to it. So firstly, why is this the best explanation? I start off at a very high level explanation first. I don't use much math, and when I do, I introduce it slowly and gradually. I tell you, I make you understand what makes neural networks so important, break down key elements in neural networks, work through backpropagation, which is something that's actually rare to find, and when you do find it online, it is a bit tricky to understand. And I walk through gradient descent, loss functions, and activation functions, all of which are very important to neural networks. And I make you understand what is actually going on in the training process, something I rarely see taught in any tutorial. So firstly, what are neural networks? Neural networks, technically, because it's just a big bunch of weights, which are just matrices with numbers, tend to be like a black box, and we don't actually know how they work. Now that's kind of a lie. We do know how they work conceptually. It is so much information sometimes stored in a neural network, we don't actually know what it knows sometimes. But essentially it takes inputs and predicts an output, just like any other machine learning algorithm. However, it's different and better than most traditional algorithms, mainly because it can learn complex nonlinear, and I'll describe what nonlinear is soon, mappings to form and produce far more accurate models. So you get better results from neural networks by far. So this is a mysterious black box. We give it a picture of a cat and it knows it's a cat. How? Same with a gorilla. Same with a dog. So let's actually see what neural networks actually do. So this is a very, very simplistic model of a neural network. It has two inputs here, and these inputs are basically like pixels in an image, you can consider them to be. These are the hidden nodes. These are basically what I told you is the black box information, the hidden area. We don't actually know what these values are. I mean, we do know what those values are, but there's so many of them we actually don't know how to actually interpret them as a human. And basically it does all these calculations in here, and then it outputs two categories, where this could be cat or dog. So as I said, this is basically the input layer here, the hidden layer, and the output layer. So in a very high level example, we can have an input layer where we're giving the neural net the color of a bird's feather, and the weight of the bird, and it tells you the species and the sex of the bird. I mean, that would be pretty cool. I don't think it exists, but it would be pretty cool. So how exactly do we get a prediction? We pass the inputs into a neural net and receive an output. So this is an example of how we actually can pass some data. Let's say it's a dark brown with white head. That's a feather color description. The weights, and we get what it actually is, a female. So here's another example of a neural net that does handwritten digit classification. So let's move on to it. This is the original input right here, and we have some hidden layers that we will talk about very soon. So basically we feed this image input here, and we get an output classification, it being 4. So this is an example of another neural net. We're going to learn a lot more later on, but this is at a high level, is conceptually how neural networks work. Okay? Hi, and welcome back to chapter 6.3, where I discuss what exactly is forward propagation. And this deals with how neural networks actually process the inputs and produce an output. So let's take a look. Okay, so you may have been familiar with this diagram, but now we have values assigned. And this may seem a bit confusing at first, but let me go through it step by step. So looking at the input layers only, we have value 0.4 going into input 1, and a value of 0.25 going into input 2. Now, in neural nets and CNNs, and pretty much all machine learning algorithms, your inputs are numerical values or categorical values. In neural nets, they're almost always or exclusively numerical values here. So now let's take a look at the hidden nodes here, H1, H2. Now you see each connection to the input. H1 has a connection from input 1, also has a connection from input 2, and you see there are two weights connected to it. What these weights are, you'll see the actual formula in the next slide. But imagine these are the weights that a neural network learns, and this is actually how these values matter quite a bit, because this is actually how it produces its output. So for now, just remember each connection has a weight, and you'll see this floating B1 here. Now, I made this for simplicity one constant for all the weights here. In reality, each weight has its own constant, but for now, let's assume everyone has the same constant here. What this is a bias constant that's added to the weights calculation here. Again, you'll see this formula, so don't be too confused yet. But just remember, these are the values or the weights that a neural net uses when processing its input. And likewise, going into the output node, there are also weights here. So each output node has two connections in this diagram, one to H1, one to H2. Their associated weights, W5, W6, W7, W8 for output 2, and also a beta constant here as well. And you see some values here named target output, 0.1 and 0.9. These targets are basically the values that we want to get our neural net to produce. However, in actual fact, we're using some random values here. So we're actually going to see what the outputs actually are. So let's calculate these values. So looking at H1 has, remember I said, had two input values here. One from input 1, one from input 2. And the associated weights here as well. So how do we get the output of H1? That's simple. That's this formula right here. And it's quite easy to understand. It's W1 multiplied by I1, which is 0.4, W2 multiplied by I2, plus B1, which is this constant I told you here. And in calculating this, you end up getting 0.8675, 0.4 by 0.2, plus 0.25 by 0.35, plus 0.7 gives you this. So that's H1's output. What we can do now is look at the formulas for each one here. H1 is this, H2 is this, and likewise the output node here, its value, is going to be in similar form here as well. It's going to be H1. Remember, this is the H1 now. The output of H1 is now the input into here. So that's W5 times H1 out, W6 times H2 out, plus B2. And similarly for output 2, it's going to be H1 times W7, H2 times W8 here, plus beta 2. This is a general formula here for every output node. So we can have multiple layers here going, and it's always going to be the sum of the weights plus the inputs plus the beta constant. So we actually have the formulas now, what this means. So you can actually see it a little bit more explicitly here. Okay, so moving on to the next slide. This is how we get H2. If you wanted to work it on your own, you could have, but I did it for you right here. And H2 was these values here, which was 0.4 by where was it here? 0.4 times 0.15, it's H2. So 0.4 times 0.15, 0.25 times 0.5 here, plus 0.7 gives you this. Okay, great. Don't know why I have it twice here. I'll have to fix this later on for you guys. So now let's get our final output here. The final output now, for output 1, is this. We take the values. Basically, remember we got 0.8675 and 0.885. 0.885 was here, and 0.8675, if you remember, was this one, H1. So we have H1, H2 inputs now, and we just multiply by the weights going forward here to get the output 1 and output 2. So these are the actual outputs we get now. However, you see I had a target in green. Output 1, we wanted it to be 0.1, wanted it to be 0.9. What does that mean? What do I mean by saying we wanted it to be these things? Well, this is very important in neural nets, because imagine we're training some data. And remember, when we use training examples, we have the inputs and we have the outputs, and we're giving it to a neural net. We're telling the neural net, this is an example. So we have 0.4, 0.25, paired with an example here, 0.1, this is the output it's supposed to be, and 0.9. And now, but in reality, when we initialize this with random values, this is what we got, pretty far off from the actual values. So what does this tell us? It tells us that the initial random weights we used for W and B produced very incorrect results. Okay? Feeding numbers through a neural net is a matter of simple matrix multiplication, as you saw. And our neural net, as you know, is just a series of linear equations. These equations here. So this is the basis of what forward propagation is. You're going to see very shortly how important basically these, let's go back to it here, these values, knowing these values and calculating the difference between our actual values and these values are. Okay? So now this is a good time to actually talk about the bias trick. Now it may confuse you, and I hope I don't confuse you too much, but the bias trick basically tells you that it's basically a multiplication tool to show you this is how neural nets do it much quicker. So remember I said we have weights coming in. These weights are the associated weights of the inputs here, okay? So imagine we have these weights coming in here. This is the xi, these are also the inputs as well. Sorry, these are the inputs, the weight inputs here, input values, these are the weights, and these are the beta constants. Now, how do neural nets actually do this calculation quickly? Well, there's something called the bias trick now. The bias trick, basically what it does, because this is not the same dimensions as this, what it does, it depends on 1 here, joins the beta constants to the W weights here, and therefore you can do a simple multiplication like this. So what this means though is that now our input vector is larger by a factor of 1, because initially, as you can see here, we had 4 input values, now we have 5. 5 basically the fifth one, the last one, being a beta constant, and allows this to be multiplied by this quite easily. Alright? Okay, so now we're going to move on to chapter 6.3, which talks about the activation functions and what deep really means. Okay, so just to do a quick recap on our last section. Alright, we saw basically that we learned about the bias trick and how we actually make this matrix calculation much simpler and faster for neural nets. We talked about how we got the weights calculations here, and we talked about basically it being a series of linear equations now. Now that keyword there is linear. Now, if you're from a machine learning background, you're wondering what makes this different to regressions or logistic regressions and SVMs, which are also a series of linear equations. Well, let's get into that in this chapter right now. So now let's talk about activation functions. So I showed you in the input nodes that it was just the input value multiplied by the weights plus the bias, and the sum of those that goes into the node is what produces the output. However, in reality, yes, that is true, but it's these WXI plus beta inputs here actually are passed into an activation function. And basically the simplest term of an activation function is that the simplest type of activation function is that this one here, a max 0 x1. What this means is that any value over 0 is going to be passed. Alright? Now I'll tell you why this is important later, but just imagine we have a function, a max function here, and we have this weights going into it. So let's see our weights. Remember we got 0.885 for H2, I believe. Let's assume our weights give us 0.75. This max function, because it's thresholded against 0, which means that anything below 0 will be negated, and you see that here. However, anything above 0 will be allowed. So that's in this example here, 0.75 is allowed. However, if the weights give us a negative value, which can happen easily, then fx is clamped at 0. It doesn't take 0.5, it doesn't take any positive value, it just becomes 0 with this activation function. So let's talk about the ReLU activation function. ReLU stands for rectified linear unit, and it probably is the most common activation function used in CNNs and neural nets. Now the appearance is quite simple, you just take a look at it. Basically it's this: it clamps any negative value to 0, so there's no negative values being passed going forward, and the forward values are basically left alone. So the forward values are x, which are always positive. So it's basically this, ReLU. So why do we need these activation functions? So remember I said if you're coming from a machine learning background, you're thinking so far without the activation functions, neural nets basically are just another form of, basically not a model, a linear model. However, having activation functions allows us to basically express the non-linearity relationships in this data. Most ML models have a tough time dealing with this. Alright, so the huge advantage of deep learning is its ability to understand non-linear models. And what do I mean by linear? Now, imagine we have two categories of data. Imagine, just for expression's sake, this is cats, this is dogs. And now a linear separable data will be easily, this is called a decision boundary, will be easily separated here. However, non-linearly separable data is going to require a much more complicated function to do. Now we can use, you may have been thinking, we can use complicated polynomial decision boundary type functions to get this. But what about if it was in more than 2 dimensions? Imagine how complicated that function is going to be that's going to separate this data. And introducing activation functions, which allows us to basically express the nonlinear relationships in data, is what makes neural nets so powerful. So there are a few other types of activation functions, some of which we may use in this course. We definitely use rectified linear units quite a bit. Sometimes we use sigmoid, sometimes we use hyperbolic tangent, but rarely ever we'll use those. And we use those in specialized cases, which you'll see later on. So, as before mentioned in the previous chapter, we have B or beta, those bias functions. So why do we need bias functions in our training? All right. Now, because you may be thinking weights can pretty much manipulate anything. However, that doesn't change much. Weights simply change the gradient. If you're from a mathematical background, you would know any value multiplied by x increases the steepness of the values going in. That's what this is here. So you can see, let's assume this weight was 0.5, 1, 2, and a sigmoid function here. So you can actually see 0.5, it's not that steep. 1 gets steeper, and definitely at 2 it's super steep here. However, what if we wanted to shift this curve left and right? We can't do that by changing the weights in front of the x here, but we can do it by adding a value to it. Adding a value actually shifts it left and right here, as you can see. So now we have the weights here, constant weights going into x, plus a constant value here, 5 by minus 1, 0, and 5. So we can actually use the weights, or the bias values, to actually shift it left and right. So let's talk a bit about the neuron inspiration behind neural nets. Why is it called neural nets in the first place? Is it a replication of a brain? Not quite. However, the activation units basically make these hidden units, or these nodes, act like neurons, because if you know how neurons work, neurons receive inputs along these nerve lines here. I believe they're called dendrites, I think. And basically when these reach a certain value threshold, the neuron fires, and the neuron's connected to many other different neurons who then receive these inputs from this neuron. That is a very similar analogy to how neural nets work. When an input value crosses a threshold, it fires. And let's talk about the deep in deep learning. Now, what do we mean by deep? Everyone says deep learning, but no one actually tells you what deep is. Deep is actually the number of hidden layers here. So this is a nice example illustration of a neural net here. These are the connections with our weights and biases. These are the nodes here, and this one has 1, 2, 3, 4, 5, 6, 7, 8 hidden layers here. Actually, you can probably count this one too as well. Sometimes you do. So this is all the hidden layers here that we don't see. And imagine now we have millions or thousands of these like parameters and all this stuff here. That gives you an example of how complicated neural nets can actually get, especially deep neural nets. Now, when do we need a neural net to be deep? Deep actually helps it represent non-linear representations in the data quite well. So if you want to actually train a complicated network, it's always better to go deep rather than shallow. However, deeper is not always easier and better to work with. Deeper networks require a lot more training time, and sometimes they tend to overfit the input data. Now, I haven't introduced the concept of overfitting yet, however, we will deal with it very shortly. So, like I said, the real magic of neural nets happens during training, because we see that it's very simple to execute a trained neural net, or a neural net with weights. When I mean execute, I mean pass an input to it and get an output. But how exactly do we get these weights and biases? This is exactly what we want to do, and I haven't told you about it yet, so let's find out. Okay, so welcome to chapter 6.4, and this is a very important chapter because we're now getting into how we actually train neural nets. And now we're looking at loss functions first, so let's begin. Alright, loss functions are essential in how we actually train and get our weight values and bias values. So let's move on to it. Okay, so first of all, neural nets have to learn the weights. But how exactly do we learn those weights? As you saw previously, our random default weights that we assigned produce some very bad results. What we need now is a way to figure out how to change the weights so that our results are more accurate. So imagine we just passed those weights, those random values in, we got the output values, we saw how wrong they were. If only we could figure out a way to use basically how wrong our values were to correct the weights inside. And that's exactly how we use loss functions and gradient descent with backpropagation. That's how they actually show their width. These are brilliant algorithms that are very, very useful in training neural nets. So it's very important that you understand these. So how exactly do we begin training a neural net? What do we need? Okay, so first of all, we need some labeled data, obviously, and that's called our data set. And it's more than some. Sometimes you need thousands, but let's say some large data set. A neural network library framework, the Keras, which is brilliant, or TensorFlow, or Tiano. Alternatively, if you want to be adventurous, you can actually use Python's NumPy and make all of this on your own. It's a really fun exercise, but kind of difficult, so I don't recommend it unless you want to challenge yourself. And patience, because training a neural net almost always takes quite a while. And when I mean quite a while, I mean simple neural net can take you an hour or two on a PC, on your home PC, but a more complicated one, you definitely need GPUs or multiple GPUs, and sometimes training time of weeks. So let's look at the training steps in the neural net step by step. Pay attention to the slide because it's critical you understand this concept. First, we initialize some random weights and values for biases. Now, technically step 0 would be have our data set, but assuming we have our data set, our labeled data set I should say, we start training by initializing random values for weights and biases. Step 2, we input a single sample of our data into our neural net, and that's called the forward propagation stage. So we pass our first input and get an output. And once we get an output, we compare our output to the actual target value that it was supposed to be. So remember previously we had target values of 0.1 and 0.9, but our actual outputs were, if I remember correctly, were 1 point something and 1 point something again, which were very off. So we need a way to quantify how bad the output values coming from these random weights were. And we call this, which I'll add an H in here, our loss. We then adjust the weights so that our loss is lower on the next iteration. What I mean by the next iteration, basically the next time we pass an input data into our neural net, we want the weights to be adjusted so that our final loss is lower. And we keep doing this for samples in our data, or batches of samples in our data set. And then eventually, basically, we send the entire data set through this weight optimization program, and we keep seeing if we can lower our loss. So, and basically we just stop training when the loss decreases. So if you're wondering what this all means here, the key thing here is we pass values to our neural net, get our loss, adjust our weights so that we can lower our loss. And the process by which we lower our loss is called weight optimization. So this is a good diagram that basically illustrates what I just said. We have our input data here. This is our neural net here, layer 1, layer 2. We have our output predictions, and we have our true targets. So now we pass our actual outputs and compare them with the values that they were supposed to be. Now, this optimizer in this green box here, which basically does backpropagation, he takes this loss value, and basically he recommends new weights, goes back into neural net, and the cycle repeats itself continuously for more and more input data. So let's see how we actually quantify this loss. As I said before, this was the predicted results from our neural net previously in the last slides. Outputs 1, outputs 2. These were the target values that it was supposed to be, and these were the actual results we got from our random values. As you can see, the difference between predicted and target is quite a bit. 1.16 is nowhere close to 2.1, and likewise, all of this is closer. So let's talk about loss functions now. Loss functions are integral in training neural nets, as they measure the inconsistency or difference between the predicted results and the actual targeted results. They're always positive, and they tend to try to penalize big errors as well. The lower the loss, the better the model. Always remember that. There are many different types of loss functions. However, MSE, called mean squared error, is quite useful and perhaps the most popular. And this is a simple formula for MSE here. Okay, so now let's actually use the MSE here to actually calculate this MSE formula to calculate our error using this error metric. So we had 1.16475 and 1.29925, and basically applying this formula to it, this is the MSE values we get here. So that is actually quite simple to execute. It's important to understand. Note that we turned our errors into positive values by squaring them here. So there are many other types of loss functions: L1, L2, cross entropy, which is used in binary classifications, hinge loss, and mean absolute error, which is similar to mean squared error. However, mean squared error, as I said, is quite popular because it's always a good safe choice. Note, a low loss goes hand in hand with accuracy, yes. However, that doesn't necessarily mean good values on training data are good. We always have to assess our loss and accuracy on the test data, which we will get some hands-on experience with later in this course. So let's see how we'll use the loss to correct the weights. Getting the best weights for classifying our data isn't a trivial task, especially when we have large image data, which has thousands of inputs for a single image. So in our simple neural net here, we just have 2 inputs, 2 hidden nodes, and 2 outputs. How many parameters are there in this? Now, this is the formula here for determining the number of parameters in a neural net. It's quite simple. It's the input nodes multiplied by the number of hidden nodes plus the hidden layers multiplied by the outputs plus the biases. So the hidden nodes here were 2. Sorry, the input nodes were 2. Hidden layers were 2. Okay, as hidden nodes, I should say. Plus 4, which was hidden layers. Sorry, plus 2 by 2, which is also 2 here, plus 2 here, plus 4, which is the biases here. Remember, each time each node here has a bias going into it. So that's how we get 12 parameters for this here. Hope that's understandable for you guys. Let's look at some more experiments here. Okay, we have 3 input layers here, 4 hidden nodes here, so that's 3 by 4 plus 4 here multiplied by 2 output layers here plus 6. Okay, those are how much weight or bias parameters we're going to have here. So 1, 2, 3, 4, 5, 6. Similarly here we'll have 8 plus 1, 4 plus 4 plus 1, which is the biases here. We'll have 3 times 4 here, 4 times 4 here, and then 4 times 1 here. So this one with this neural net, this simple neural net with 2 hidden layers here, with just 4 nodes each, has 41 learnable parameters. So now let's get into training part 2, which is backpropagation and gradient descent. Okay, so on to training part 2, where I discuss backpropagation and gradient descent. This is basically how we determine our weights in an efficient and effective manner during training. So what exactly is backpropagation? So what if there was a way we could use those loss values we just saw in the previous section to determine how to adjust the weights? And that is the brilliance of backpropagation. Backpropagation, it's a bit tricky to say sometimes. Backpropagation tells us how much we need to change our weights in order to change the loss, to affect the overall loss. So let's see how that works. So revisiting our previous example, okay, remember this diagram, all targets, all our values and stuff. So using the MSE obtained from the output 1, backpropagation allows us to know if changing W5 from 0.6 by a small amount to, let's say, 0.6001 or 0.5999, that's basically a 0.001 addition or plus to this weight. How would that affect the overall loss? Would changing W5 increase my loss or decrease my loss? That is essentially what backpropagation tells us. So now we then backpropagate this loss to each node, right to left, so we keep moving backwards to determine the direction the weight should move, negative or positive. So imagine we calculated backpropagation tells us W5 maybe should have been positive, and then we go back, then we do it for W7, W8, W6, then we go back again, we're working backwards, right to left. So how much should we adjust this, and this to lower our loss? And that process basically of working backward from the output is called backpropagation. So let's go over the full cycle. Therefore, by simply passing one set of inputs of a single piece in our training data, we can now adjust all the weights to reduce this error or loss. What do I mean by this? So go back to the previous slide. By passing one input data here, 0.4, 0.25, and getting the loss values here, we can now use backpropagation now to adjust all the weights going back so that the next time we have an input data coming in, loss should be less. However, this tunes the weights for that specific input data. But how does that make our neural net generalize? So I'm pretty sure you were thinking that was the reduction in weights for that particular piece of input data for these values here. But what if our next input data is 0.5, 0.7, and the targets are different? Will those weights be better or not? That's a very good question. But however, doing this for all the training samples in our data, we effectively, by just keep giving it more and more examples, and remember this data basically has some sort of structure to it, so essentially by just keep passing more inputs into our neural net using backpropagation to keep adjusting the weights, eventually our weights keep getting better and better, and by better I mean our loss values coming out of the output nodes here, when minusing from the target outputs, is becoming less, will be becoming less and less. So every time we send a full batch of our training data into this, it's called an epoch or iteration. Now this is a difference here, and we'll discuss it soon. An epoch essentially, actually I'll tell you right now, an epoch is when we pass the full data set, full training data into our neural net. That's one epoch. And an iteration sort of means the same thing, but it could be different. But remember, epoch is what's important here. So we just went through essentially what backpropagation is in a very high level. Now, what about gradient descent? What exactly is gradient descent? Now, by adjusting the weights using backpropagation to lower the loss, we are performing gradient descent. And gradient descent is essentially an optimization solution. This adjusting the weights to lower the loss is essentially an optimization problem. Okay? So backpropagation is simply a method by which we execute gradient descent. So always remember that. People say we're doing gradient descent. What are we doing? We're optimizing our weights to reduce our loss. So, but why is it called gradient descent? What even are gradients? Now, if you remember correctly from your high school maths, gradients represent a slope at a point on a function. So, and it actually tells you the direction the function is moving. So at this point here, it's a positive gradient. This point here, slope is going downward, so it's a negative gradient. And at this point, there's no change, so it's a zero gradient. So by adjusting the weights to lower the loss, we are performing gradient descent, which I previously said. And gradients, as I just said, are the points of direction on the curve here. So, a bit more about gradient descent. Now, performing gradient descent on these functions here could be a bit tricky sometimes. And why is that? Imagine our function looks like this. And we're trying to find this. This is actually our real function. Like let's just say this is a real representation. I know it's a 2D thing, but if you try to visualize it, that is what a neural net is. It's basically, we have this multidimensional function that we're trying to get. And by getting, what I mean is that we're trying to adjust the weights so that we get we basically try to adjust the weights so we lower the loss to get this function. So, but what if now, these are points here where there are minimas, maximum and minimum points, if you remember from your math class. These are called local minimas. Why are they local minimas? Because they're just in this section of the curve, they're basically the lowest point in gradient. However, the global minimum, which is the actual minimum gradient, minimum point here, is here. So oftentimes when training, you hear the term, we tend to get stuck in local minimas. That is this here. That is when we're adjusting our weights sometimes by too larger values, and that you'll see that parameter called learning rate afterward, which is how much we adjust these things by. All of this will be explained in the next chapter when we actually do a worked example of backpropagation. But essentially what we're trying to do is find the global minima. This is the true point in our representation that gives you the lowest loss. So a good example is, imagine a bowl, and we're moving in random directions along this bowl, traversing it, and this bowl is rough, as you can see, and we're trying to find the global minimum point, which would be at the bottom here. However, in moving around, let's say we keep jumping, and we don't find it. So we need to jump in small steps to actually find this point. So that brings us to stochastic gradient descent. So naive gradient descent is computationally very expensive and slow, and it requires exposure to the entire data set, then it updates the gradient. That is, if you actually do that in real life, that is super slow. Don't do that. Stochastic gradient descent does updates after every input of a sample. So like I said, we input one sample of data and we adjust the gradients immediately using backpropagation. Sorry, the weights immediately using backpropagation. Now, what would this do? This would produce very noisy, fluctuating loss outputs in reality. And again, this can be slow. You'll probably see changes quickly, but they'll almost appear random. That brings us to mini batch gradient descent, which is effectively a combination of the two. Instead of passing your entire data set, like in naive gradient descent, we basically take batches of the inputs, and then we pass that batch through our network. Then we use the backpropagation to adjust it, and basically that is actually how we update our weights here. Now, there's no specific rule in how big batches can be. They can actually be less than 20. I tend to use 16 sometimes. But generally, batches, it depends on how much data you can fit into your RAM at that point, or your VRAM if you're using GPUs. And basically this leads to a faster training time, faster convergence to the global minima. Whenever you hear the term convergence, we're basically trying to find basically the ideal number of weights where our loss stops decreasing. So in this section, let's just do a quick overview. We've learned that loss functions such as MSE, mean squared error, tell us how much error our weights have produced. Then we then use that error to perform backpropagation, which is then used to lower weights in the next cycle or next time we input data. And this process of optimizing or lowering the weights is called gradient descent. And an efficient method of doing gradient descent is called mini batch gradient descent. Okay, so now in the next section, we're going to actually do a worked example, doing some actual math here, of backpropagation. So stay tuned. Okay, so now this brings us to backpropagation, an actual worked example. So let's get to it, and you actually get to understand exactly what backpropagation is doing. So from the previous section, we have a good idea of what backpropagation is, at least at a high level. And to reiterate, it's a method of executing gradient descent or weight optimization so that we have an efficient method of getting the lowest possible loss. So how does this black magic of backpropagation actually work? Okay, so let's do a simplified explanation again. So we obtain a total error, that was the loss, the mean squared error, at the output nodes, and then propagate these errors back through the network using backpropagation to obtain the new and hopefully better gradients or weights. So what happens here is that we get a loss, and then we send the loss back in here. And when I mean send it back in, basically we're applying backpropagation to this loss, and now it's going back here. We're calculating and updating the gradients or weights here, and then doing it again with these nodes. So backpropagation is simple, and it's made possible by the chain rule. So what is the chain rule? So without making this too complicated, essentially this is the chain rule here. We have two functions, y is equal to f of u and u is equal to g of x. Okay, just two functions. I know it's going to be confusing at first if you don't know much math. However, basically the differential of how y changes with respect to x here, its rate of change, is given by this. These cancel out, these two du's. So we end up with this. That is effectively the chain rule. Now, if you really want to understand the chain rule properly, you can go back to there's lots of websites that explain it in more detail. I'm not trying to get into too much detail here. I'm just giving you the chain rule defined as it is here. So let's look at this. This is our previous NN here with all our confusing values and formulas. We use the chain rule to determine the direction the weights should take. So let's see how it's actually done. So remember, H1, we just cut it out from this point here, going into one of those nodes. So we have the node output 1 we're looking at. So this is the bias constant here going in. These are our weights here. And this is basically how we get output 1 here from this formula, from this. So again, let's take a look at W5, and I've highlighted it here. How do we change W5 so that we affect the error at this node here? Should W5 be increased or decreased? Well, let's find out. So our calculated forward propagation and loss values here, just to reiterate what they were from the previous section. This is it here, H1, H2, output 1, output 2, and I haven't mentioned this before, but basically output values here, we apply a logistic function that squashes them between 0 and 1. So what that means is we have our outputs previously being, do I have them here? No, but remember they were 1.1 something and 1.2 something, I believe. And basically when we apply a logistic function to here, these are the values that we actually get here. So we took that 1 point something and we squash it to a value between 0 and 1 using this function. That's the actual outputs here. Okay, so moving on to the next slide. So now we do a slight change in the MSE function, and that change basically just adding a half constant, multiplying it by the error, mean squared error here. And that basically is just to make it look a little bit nicer when we differentiate it. It doesn't really impact the overall MSE much because it's a constant. And so updating our values previously, this is our new MSE loss, applying both the logistic squashing function here and MSE as well, okay, the new MSE. So let's explore W5. How much do we change W5 by to basically lower the entire loss? And that's what this formula is here. We want to know how much changing W5 here impacts the total error, where E total is the sum of error from output 1, output 2. So I'm not going to get into exactly how we get this equation here, but this is basically using the chain rule to calculate W5. So how much the total error here changes with respect to W5 is given by the differential of E total over the output 1 multiplied by the output 1 over the net output here. Differential of it, sorry, it's partial differential. And this as well here, how much this output 1 here changes, net output 1, with respect to the change in W5. So these are the three pieces we need of the chain rule to get this. Now let's look at this here, E total. E total is basically half output 1 output here and output 2 here. That is how we actually get E total. Because remember, going back to the slide, we know the output 1 here, what his predicted value with our random values were. So his predicted value was something, his target value was something else. So we just basically apply what output 1 here is for output node 1 and add it to this mean squared error of output 2. That's how we get E total. So now let's differentiate E total here with respect to output 1, okay? Because that's what the first term in our chain rule here is. So this gives us 2 by a half, which cancels off to be 1, 2 minus the exponent 1, and since this has no output 1 here, this basically is treated as a constant, so the differential of a constant is 0. So simplifying this, we get this, and we actually have the values of this. We have the output 1, which was, let's go back to it, 0.7 here, and we have the actual target value, which was 0.1. So E total of output 1 is 0.64. Brilliant. So now let's get the second term here, which is differential of output 1 over the net output 1. Let's see what that exactly means here. So net output 1 is basically the application of the sigmoid function for it there, for the output 1 node. Remember, we apply the sigmoid function here to the outputs. So let's go back to it now. So how do we differentiate this? Now, fortunately, the partial derivative of a logistic function is the output multiplied by 1 minus the output, which is this simple thing here. So now we have this value, 0.742. Let's go back to see how we got it. That's output 1. Just to reiterate, that came from here, output 1. Now, I know I'm going a bit too fast for most of you guys to keep up. This actually took me a couple hours, embarrassingly, to work through, 2 hours. So take some time if you want, print out these slides or have them up and work through them. If you really want to get a proper understanding of this, just work through them on your own, okay? So that gives us this 0.74, 1 minus 0.74, which gives us negative 0.191293. So that's now our second term in the chain rule. So let's go forward, get the third term now. Third term was differential of the net of output 1 over differentiated with respect to dW5. Alright, so net of output 1 is this here, W5, that was this input, if you can visualize it here, times the output of H1 plus W6 times the output of H2. Should have probably had a drawing of it here, but we can just go back to it quickly if you want to just see it. That's this here, this formula right here. So let's differentiate it with respect to W5. So differentiating it here, we just get this term here, 1 by this, because this differential of this would be 1, plus this is a constant, this is also a constant here. So we just end up with a simple output H1, which 0.70 which we know from, let's go back to it here. Or where is it? This is it here, H1. Okay, output of H1 is 0.704225234. So now, as we can clearly see, we have the tree terms for how much E total is supposed to change with respect to D5. Alright, so that's this formula here. We multiply our D3 terms and we get this. Now, what exactly does this tell us? We got 0.086526. Well, what does that tell us is that the new W5 is going to be that minus this. Now, you see we introduced this new constant here, this new parameter. And this parameter is called learning rate. Now, before I get into learning rate, let's just assume that this wasn't here. So the new W5 would just be the W5 term minus this term here. So minus 0.08625 here. So if we were to update it straight away, it would just be 0.6 minus 0.08 something, which would give you 0.52. However, we have a constant here called learning rate. Now that is a very important constant, and I'll tell you why. If we set the learning rate here at 0.5, which is actually quite large for learning rates go, okay? But the reason for that is we don't want to update our weights when too big a jumps. We want to know the direction it's supposed to go. So in this case, the direction was supposed to be less than 0.6, so we get 0.55 here. But that's after applying the learning rate. However, in reality, we don't actually want to change it even by that much. This was just an example I used for you guys, but in reality, learning rates are like 0.0001. So we want to just go a smidget, a tiny bit amount, in the direction W5 is supposed to go. And there's a reason for that. The reason for that is because if we're changing our weights by such large amounts, we tend to skip over the actual global minimum. That's why I mentioned it down here. We overshoot the global minimum. So instead of getting trapped in a local minima or just jumping around entirely, we adjust the weights by very tiny amounts so that we could converge exactly to the global minima. It makes training much longer, but we always get a much better model out of it. So this parameter learning rate, now if you look at carefully at the first formula, it controls it by a big magnitude here, which is why I said we always use a very tiny value. So I hope that explains learning rates to you and backpropagation to you. This was a bit tricky to understand. Sorry. But I think this is a very helpful for your intuition behind backpropagation and how we adjust the weights. And if you want to do some homework on your own, you can use the same formulas to calculate W6, W7, W8. I did them manually myself. Took quite some time, but you can check it out and see if these are correct. So just to give you a bit of a heads up, the W1, W2, W3, which are the nodes prior to the other nodes, basically the second stage of backpropagation, this is the formula here, fit, going forward. Okay, so similarly, you can actually calculate W1, 2, 3, and 4 using the same method I just showed you. However, they are slightly different. They involve a bit more work. So I'll leave this as an exercise for you. You don't necessarily have to do it, to be fair. Just understand what you're doing. This is the actual formula for it. So play around if you want and go get into it. Okay, so that concludes this chapter on backpropagation, a worked example. I hope you found it very useful for you. So let's move on to regularization, overfitting, and generalization, and understanding what test data sets are and how do we know if our model is actually good. Okay, so welcome to section 6.8. I actually just corrected it from the last section. I had a 6.7 here, my bad. So this section deals with regularization, which is a very important concept. Also, you're going to understand what overfitting is and why it's bad and why we need to have our model generalize well, and you understand basically what are test data sets. I think I mentioned it previously, but I'll go into it a bit more here. Effectively, we want to know when and how our train model becomes good. So what makes a good model? Now this is a very basic explanation of what makes a good model. Good model is accurate, generalizes well, and does not overfit. Now both of these kind of mean the same thing, and you'll understand that shortly. And I deliberately made this slide vague because accuracy all depends on your domain you're looking at. Sometimes you want 99.999% accuracy. Sometimes you can be happy with 80% accuracy. It all depends on your application. So let's look at three models here. Let's look at these two classes, one in green, one in blue. And this is model A, model B, model C. The red line here is basically the decision boundary for each set of data here, for each model I should say. So what is happening here is that how do you know which model, like intuitively, what would you say is the best model here? Now let's look at model A a bit closely. Model A actually separates all the data accurately. It sees a blue ball over here and actually adjusts its decision boundary to encapsulate it. Model B basically doesn't do that. Model B basically does a nice smooth curve here. It doesn't push itself all the way out here to capture this blue ball, and basically it forms a nice clean decision boundary here. Model C takes a much more simplistic approach, giving you a straight linear line separating these boundaries here. Now what would you say is the best model here? Now I would say B, and I'll tell you why. Even though B doesn't capture this blue ball here, as you can see from the nature of this data, the blue ball technically is in the green zone. Yeah, so this ball here is an anomaly. He's basically an outlier. He may have ended up here from being mislabeled. Maybe he was supposed to be a green ball, or maybe he's just highly unusual. And generally, we don't want our models to basically cover this blue ball here. This is called overfitting, and it's bad because in most likely case, or most likely scenario, the green balls are going to be right here. So what happens when a green ball is here, like an unseen green ball in the future, but we feed this green ball his XY coordinate that is right here into this model. This overfitting model is going to label it as blue, unfortunately, when in reality, if you see it here with this nice clean model B boundary, it is supposed to be green, the green class. So that's an example of a model that is overfit, probably too complicated for its own good, as opposed to model B, which generalizes well. Model C, on the other hand, is way too general and is not going to be a good model. So, as I explained before, this model overfits, this model is ideal or balanced, and this is what is called underfitting. He doesn't fit the data too well. He just gives you a generic little boundary and tells you, yeah, I tried my best, but it's underfitting. So let's go into overfitting. Overfitting is what leads to poor models, and it's one of the most common problems faced in AI, machine learning, neural nets. It's a problem I face continuously when training my convolutional neural nets. It always happens, it always tends to overfit on the training data, and we will experience that later on in this course. But what it means basically is overfitting is when our model fits near perfectly to our training data, as in he has very high accuracy on the data he was trained on, maybe even high 90s or 99.9 something. However, on the test data set, which is the unseen data, he is going to be performed poorly because he's now basically modeled after the training data but can't generalize well the data he hasn't seen. So that's what happens when you try to pass a new point to this position here. Exactly what I mentioned before. Its true color is supposed to be green, but it will be classified as blue. Models don't necessarily need to be complex to be good. They need to generalize well. So, how do you know if you're overfit? Well, that's why I mentioned test data previously in the beginning of this slide. We need to test our model on test data. And in all machine learning algorithms and stuff, we always use a test data set. And basically, if we have entire data sets, say for 1,000 images, we take 700 and we train on those 700 labeled images, and we reserve 300 as test data. That 300 is critical because it tells us how well our algorithm or model performs on data the model has never seen before. This is a very common case sometimes with overfitting. 95% plus accuracy, but on test data you get like 70%. It's a perfect example of overfitting. So overfitting illustrated graphically. Here's what happens. Remember I mentioned epochs? Now later on in this chapter, I discuss exactly what epochs are. It's basically every time we send the full training data set into our training algorithm, we have completed one epoch, and we need to train for maybe hundreds of epochs sometimes to get a good model. Usually that's not the case. Usually you can get away with training 20 to 100 epochs, but generally that's what we have to do to get the best models. So this is an illustration of what overfitting looks like. So look at the training loss here in red and accuracy. Loss is going down quite well. Accuracy is going up close to 100%. The scale of the accuracy is on this side and loss is on this side, and epochs are to X. And now look at the test. The test loss basically just fluctuates between 1 and 1.5 and actually goes up in the end. It's not good at all. And look at our test accuracy. He's hovering at abysmal rates of like below 50%. And while his training data is at 100%, that is this is actually extreme overfitting, to be fair. It doesn't actually ever get this bad. At least I've never gotten it to be this bad. But it's a good example of what we actually see happening in the real world. Good training accuracy, poor test accuracy. And that's overfitting. So how do we avoid overfitting? Now there are many techniques to avoid it, and I'll discuss it soon in this slide, in this section. Now, overfitting is a consequence of our weights. Our weights have been tuned to fit our training data, but don't fit. They're overtuned in a way so that they don't perform well on test data. And we know our weights are a decent model, just too sensitive to the training data. So is there a way to fix this? What I mean by too sensitive, I mean it's just optimized exclusively for our training data. So we can avoid overfitting by using a smaller, less deep model. Deeper models can sometimes find features or interpret noise to be important. Noise was an example of this here. This clearly wasn't that important, but yet a deep model will actually try to figure out and model this. So that's because due to their deeper abilities, deeper networks have abilities to memorize more complicated features. And that's called the memorization capacity. But there's another way, and that's called regularization. I don't often recommend, or I shouldn't recommend, using less deep models to get better results, because there are other ways around it, and you want to actually always have a deep enough model to represent complicated patterns in your data. So let's see what techniques we can use to regularize. So what is regularization? It's a method of making our model more general to our data set. So basically, regularization will take a model that produced a decision boundary like this and sort of tweak it so that it becomes like this. And let's see. Now, it's not actually doing it. That's the actual term of regularization. We basically want to get a model like this and not like this. And let's find out how we do that. So there are a few types of regularization. There are actually more than this, but these are the basic types. There's L1, L2 regularization, cross-validation, early stopping, dropout, and data augmentation. So let's look at L1, L2 regularization. These are techniques that we use to penalize large weights. Large weights of gradients manifest themselves as abrupt changes in our model's decision boundary. And by penalizing them, we're effectively making them smaller. L2 is known as ridge regression, L1 is lasso regression. Now, there's a lot more theory behind these things here. I'm just basically showing you the formulas of what they actually are. So, as you can see, this is basically what ridge regression, or L2, is here. This is our MSC here, but we're actually doing something with the weights here. What are we doing? We're applying a constant here over 2, and the sum of the weights squared. And L1 is not squared, it's just the absolute value of the sum of the weights. So this parameter here controls the penalty we apply. So via backpropagation, the penalty on the weights is applied to the weight updates. So the difference is that between them basically is that L1 brings the weights of unimportant features to 0, thus acting as a feature selection algorithm. You may not know what feature selection is, but if you want to know what feature selection is, it's basically trying to find out, we have like 20 inputs, what input is the most important to our output. Okay, that's also known as sparse models as well. Whereas L2 penalizes it even more. It doesn't bring it down to 0 though, okay? So effectively what we're doing here, just remember, L1, L2 prevents our weights from being too large so that we don't have abrupt changes in our model. Abrupt changes basically mean things like, go back to here. We basically try to make this smoother instead of having this abrupt gradient changes here. So let's go into cross-validation. Now cross-validation is something I rarely ever use because I'm just not that used to using it. I used to use it a lot doing previous machine learning stuff, but in deep learning I don't use it often. But if you want to know what it is, it's quite simple actually. Basically, cross-validation, or also known as k-fold cross-validation, is a way we split our data set, our training data set, into different folds, and we train on those folds, and we basically test on the other folds afterward. So let's look at this here. This here is our test fold here, our validation set, and our training set. So what happens is that we train on these 4 folds here, and we test on this. Then we train on these 4 folds here, we test on this. What this does is that we don't actually have any unseen data in this model. What we're doing is just we're continuously testing on segments of the data, and then training on segments of the data, and then testing on a different segment. It reduces the overfitting, yes, but it also slows down the training process. Now, early stopping is something we can actually automatically do in Keras. Basically, we can set something in Keras that tells us if our loss stops decreasing, stop training. So if we set our model for 100 epochs, but say at epoch number 30 something, the loss stopped decreasing, it's going to stop training somewhere around here when it realizes that. And it's going to give you this model here, the one with the best loss. The reason we do early stopping is that sometimes if we keep continuously training over and over number of epochs on our training data, it tends to basically overfit on that training data. So we need to actually stop it early sometimes so that overfitting does not occur. And let's talk about dropout. Dropout is actually very easy to implement and extremely useful. So dropout refers to dropping nodes, both hidden and visible, in a neural network with the aim of reducing overfitting. What do I mean by dropping nodes? What this means is that in the training process, certain parts of the network are ignored during the forward and back propagations. This is a way of actually making our network have some redundancy in a way, but what it also does is that it actually adds regularization to our networks. It helps reduce the interdependency between learning, or neurons while learning. So it actually leads to more robust and meaningful features. So in dropout, there's one parameter we use, it's called P, and P is the probability that the nodes are kept or dropped out in the training process. So the only consequence of using dropout though is that it almost doubles the training time to converge during training. So this is a good illustration of dropout. This is how a standard neural net works when we train it. And after applying dropout, let's say this is a fairly high value, these nodes here are ignored, and these nodes here are used in training. And lastly, well, it's not the last method of regularization, but it's the last one I will teach in this course because the others are actually quite exotic and not commonly used. So this one is called data augmentation. Remember I said you need lots of data to train a network? What if you don't have? Well, in computer vision especially, it lends itself naturally to data augmentation. What we do is we take our input data set, we have one picture of a dog, but how about we just make some manipulations to this image? We can rotate it completely. We can, I think this one is just mirrored back here, and this one is actually zoomed in a bit as well. So that is a way we can actually expand our data set. So in this section 6.9, I discussed some terms I've used before, terms such as epochs, iterations, and batch sizes. I'll discuss it a bit because a lot of times in tutorials and in lectures you'll hear these terms being used, and sometimes they'll be mixed up, and I'll tell you why afterward. So epochs. Now I'm sure you've heard me mention it quite a few times before. So what exactly is an epoch? An epoch occurs when the full set of training data is passed or propagated and then back propagated through a neural network. So the process of one epoch means that we've trained our neural network on our full data set and updated all the weights. So after the first epoch, generally, we will have a decent set of weights. However, it's never enough. You need to train for several epochs over and over and over to continuously updating the weights so that we converge. And by converge, I mean get the lowest weights, get the lowest loss possible with those set of weights. Now batches. Now, in every time you train in Keras or any CNN or any neural net, you'll see they specify how much batches do you want. Now, batches aren't super critical like batch size. It doesn't generally affect your results that much. But what you need to do though, the bigger the batch, generally the better. However, you're limited by your RAM or video RAM if you're using GPUs. You can't put all the data at once into a batch, so you need to split it up. So generally if you're using image data and it's basically resized to something like say 100 by 100 pixels, you can use a batch size of maybe 16 to 32, depending on how much RAM you have. I'm assuming you may be using at least 4 to 8 gigs of RAM, so a batch size of 16 is generally quite good. So actually, I failed to mention one thing though. If your batch size is 1, you're effectively just doing stochastic gradient descent, which is not a very effective way of doing gradient descent. Mini batch gradient, I believe that's the name of it. But using mini batches is basically the best process to actually train and implement gradient descent. So what about iterations? I used to get confused between iterations and epochs quite a bit. However, the difference is quite simple. Iterations are just simply how many batches we need to complete one epoch. Now, the reason I used to get confused for was because I had a professor who would say you train your neural net for 10 or 100 iterations. And that was because I think he was using MATLAB to train. And in MATLAB, at least maybe in the library he was using, iterations were actually meant as epochs. And I don't even know what epochs actually were at that point. They were just iterations. But I mean, I don't even know what iterations were called. Maybe they were called batches or mini batches, perhaps. So, in our previous example, which on this page I didn't actually discuss, but let's say we had 1,000 samples of data and we specified a batch size of 100. That means you'd be taking 100 samples of that data in each pass in the network to update our weights. So we have 10 basically iterations to complete one batch, as I said right here. So that's it. So now let's move on to how we actually measure performance and understanding the confusion matrix. So welcome to chapter 6.10 or chapter 6.10, where I basically explain how we assess and measure performance of our trained model. As you will learn, there's a lot more than accuracy to determine the model's performance. So we've seen this graph before. This is basically the graph illustrating overfitting, and it was a pretty bad model here. It overfitted quite a bit, but it was very good in the training data. But that's not what we want at all. So let's talk about loss and accuracy. It's important to realize while loss and accuracy represent different things, they're highly correlated, so they're essentially measuring the same thing, the performance of our neural net on our training data. Now, accuracy basically is just a simple measure of how many correct classifications we got over the total number of classifications overall. So let's say we were predicting whether something was a cat or dog, and let's say we got it right 99 times out of 100. That would be a 99% accuracy. Now, loss values tend to go up, not tend to, they will go up when the classifications are incorrect. That is different to the expected target values. So basically, as I said before, they are correlated. So is accuracy the only way to assess a model? No. There are actually other ways, and I'll discuss it too here. So accuracy is important, yes, but it doesn't tell us the full story. So let's look at this example here. Let's say we're using a neural net to predict whether a person had a life-threatening disease based on a blood test. Now, you would think they are yes or no are the basically possible answers. However, those are the answers yes, but those are not the actual scenarios that happen in real life. In real life, or in reality I should say, these are the 4 scenarios that can happen. It can be a true positive, which means that the test predicts positive for the disease, and the person has the disease, so that's good. It can be a true negative, which is the opposite. Test predicts negative, and the person doesn't have the disease, good. However, it can be a false positive. Test predicts yes for a disease, but it didn't actually have the disease. So it's not good, but not as bad as this one, where it predicts negative for the disease, but the person actually had the disease. So let's take a look and see how we use these 4 scenarios to assess the accuracy of a model. So I'm not sure if you've ever heard of these terms, but there's recall, precision, and F-score. Now recall is defined as this: number of true positives over the number of true positives plus the false negatives. If you remember correctly, false negative is this here, and true positive is this here. So what recall is telling us is that how many true positives did we get? So how many times did we accurately predict that a person has the disease over how many times the person actually had the disease? So that's what the denominator in this is. How many cases of the diseases were there, and how many times did we get it right? That is effectively what recall is. Now, precision of all our samples here, how much did the classifier get right? That's what precision measures here. So we have, again, true positives here over true positives plus false positives. So let's go back, to false positives here. False positive here is basically the test predicted positive, but the person didn't have the disease. So that's the denominator here. So how many times did how many of all these samples, how much did the classifier get right? And F-score is an attempt to actually measure both recall and precision in one. Okay, so let's take a look at an actual example here. So let's say we've built a classifier to identify gender, male versus female, in an image, where in this image there were 10 male faces and 5 female faces. So we run our classifier on this image and it picks up 6 male faces. Now, out of those 6 male faces, 4 were actually male and 2 were female. So how do we work out our precision? Now go back to the formula. Our precision is number of true positives, which was 4 in this case, because we got 4 male faces right out of the 6. And how many same true positives plus false positives. So how many false positives were there? There were actually 2 false positives, because it picked up 2 females here, but told us they were males. So those were false positives. So that's 4 over 6, so 66%, 0.66. So let's work out our recall now. Our recall is the same, true positives over true positives plus false negatives. Now, what's the false negatives here? The false negatives here were the fact that 6 male faces. Remember, a false negative in our other example was how much tests for disease did it miss. Okay, so in this case, there were 6 male faces that were missed. So it's true positives over true positives plus false negatives, which is 0.4, 40%. So now applying our F1 formula, this here, 2 times recall times precision over the recall plus the precision, that gives us this, and that gives us this final value, which is close to 0.5, which is 0.498. So that's a good example of how recall and F1 and precision are used to actually assess model accuracy. Now, this isn't actually used that often in CNNs, but I actually do use it quite a bit in some models. I shouldn't say it's not that much used. I don't see it used that often in a lot of other researchers. I'm not entirely sure why, but to me it depends on the application. So if you're predicting something very important, you need to use this to understand your performance. How well is our model actually picking up stuff, and what kind of mistakes is it making. Okay, so it all depends on the domain. So this is a good example here from Wikipedia. It actually illustrates the true negatives, false positives, true positives, false negatives in a little Venn set diagram here, selected elements. So you can actually see the formulas applied here visually. So you can take a look, pause the slide and take a look and try to understand it conceptually as well. So hopefully this helps. The point of this chapter was to actually show you that accuracy and loss are not the sole metrics we use to assess performance. So now let's go on to a review of everything we've just learned. So you've spent over an hour basically going through neural nets in some detail. So I think it's about time we actually do a review and basically try to reiterate everything we've just learned. So let's move on. So let's go over training again. So just to reiterate the steps, we initialize some random values for our weights and biases. We input a single sample or a batch, perhaps, of samples of data. We then compare our outputs with the actual target values. We use those loss values. We use those values now to calculate our loss values based on a loss function here. We then use backpropagation to basically perform mini batch gradient descent to update our weights. Now it doesn't have to be mini batch gradient descent. It can be stochastic gradient descent or naive gradient descent, but mini batch is perhaps the best. And then we keep doing this for each batch of data in our data set. And each time we process a batch is called an iteration until we complete one epoch or an epoch, which means that all our training data was fed into our model, and we use backpropagation to update the weights. And then we just keep performing more and more epochs and stop training when accuracy or on our test data set stops decreasing. So again, this is the training process visualized. I think we went through this before, but just again, let's do it quickly. Input data comes in, or a batch of input data. We get the predictions, compare them to the true targets. We use a loss function to assess how different they are. Then we get an optimizer, and we use backpropagation or stochastic gradient, which basically performs stochastic gradient descent of any other form to update the weights. And then we keep doing this again and again for more and more epochs. Okay, so these are some general best practices I find that are quite useful to use when training neural nets. Definitely use ReLU or leaky ReLU. I'll explain what leaky ReLU is in later slides. Loss functions are definitely, you should always use MSE or some variation like mean absolute error. When you're doing regularization, I always recommend you try to use at least L2. Definitely use dropout, and it's not stated here because this is for neural nets, but generally always use data augmentation if you're training CNNs. Learning rates should be low. 0.001 is a good value to use. We talk more about learning rates in later slides, so for now, just remember 0.001 is a good learning rate to start off with. Number of hidden layers depends on the performance of your machine, honestly. I mean, I would go as deep as you can go, however, that can exacerbate and lengthen your training time so much. So don't try to be too adventurous. Keep a model that you can train fairly quickly on your machine, and that will allow you to experiment a lot, as opposed to training a model for days and then realizing something is set badly and you're not getting performance you want to. And the number of epochs, you should always try to train for at least 10 to 100 epochs. After generally 20 epochs, you can kind of get an idea of how your model is performing. So once you can start off training maybe 20 epochs to 30 epochs at first and adjust your parameters to suit, and then your final model, you want to actually make the best, train it for at least 50 epochs. Okay, so that brings us to the end of our neural network section. Now, a lot of other courses and textbooks and blogs will talk about different types of neural nets and all sort of exotic stuff, but to be honest, you need to understand the core, which is what I just showed you. The core being gradient descent, backpropagation, how training is done, and how to assess your performance effectively, how to avoid overfitting, understand when you overfit as well. So you now have a very good core understanding of neural nets. And now we can begin moving on to chapter 7, which is on convolutional neural nets. The real deal about this course is actually on convolutional neural nets, which is what we'll be training many in Keras going forward. Okay, so welcome to the big famous chapter in this course on convolutional neural nets. This is basically the core of the course, so please pay attention to this chapter. You're going to get a very good explanation on convolutional neural nets, I guarantee it. So what does this chapter include? Let's see. Firstly, I do a brief introduction to convolutional neural nets, or CNNs for short, because that'll save me a lot of time to say that word. So we talk about convolutions and image features in the next chapter. Then depth, stride, and padding. You'll understand that soon. What ReLU is, which we talked about ReLU before, but how it applies to CNNs now. What the pooling is. What a fully connected layer is. And how we train CNNs. And lastly, how to design your own CNNs. So, I hope you're looking forward to this chapter. It's going to be fun, and you're going to learn quite a bit. I guarantee it. Hi, and welcome to chapter 7.1, where I introduce the concept of convolutional neural nets, basically CNNs, as I'll be referring to them throughout this course. So, why are CNNs needed? We spent a while discussing neural nets previously, and you may be wondering, why would we have spent so much time on neural nets if we're now just going to suddenly discard them and go into CNNs? Well, understanding neural nets is critical in understanding CNNs, as they basically form the same foundation for all deep learning types of networks. All of them basically require you to understand stochastic gradient descent, backpropagation, the training process, batches, iterations, all of those things. Basically, CNNs are just a different form of neural nets, and you'll find out why and how and why. So why CNNs? Mainly because neural networks don't scale well to image data. Remember in our intro slides we discussed how images are stored, which was basically this. You have a grid. Let's say this is a 10 by 10 grid here. So we have 100 inputs here technically, and each input has 3 different colors, so that's a lot of data. And the grayscale version of this as well. Okay, and RGB would just be this. So as I said, neural nets don't scale well to image data. And why is that? Let's consider an image, color image, a small color image, 64 by 64 pixels. So how many inputs is that? 64 by 64 times 3. That's 12,000 inputs already for what is a tiny image here. So therefore, input layer will have at least 12,000 weights, and that is large. And basically, if we even go higher, we'll have 90,000 weights in the input layer alone. And that's not even considering how many more parameters we'll have in the hidden layers as well. So we need to find, basically, a CNN doesn't actually reduce the weights in the beginning on the input. What it does though, it finds a representation internally in hidden layers to basically take advantage of how images are formed, so that we can actually make a neural net much more effective on image data. Let's see how this is done. So, introducing CNNs here. This is effectively what it is here. I'm going to go through each of these in detail in the later slides, but for now, conceptually, this is what it is. Remember in neural nets you had an input layer and hidden layers? Well, these are the hidden layers in a convolutional neural net. What happens first is that we have what is called a convolution, where ReLU activation unit is applied to the convolution here. And this convolution here, it slides across the image here, producing values here. Don't worry if you don't understand this just yet. I'm going to go into detail into each one later on. So just feel free to just basically look at this, get familiar with the terms and the diagram, how it looks, but you don't actually have to know what these are yet. So this is what convolutional neural nets look like. So why 3D layers? I didn't mention 3D layers here before, but you can see here that there are depths of layers. Stacks going this way and this way, whereas neural nets were represented in more of a flat diagram here. So 3D layers allow us to use convolutions to learn image features. And by learning image features, you'll get to understand what image features are very soon. And therefore, this allows us to use far less weights in our deep network, allowing for significantly faster training and a lot less parameters to learn. So this is an arrangement of how neural nets use 3D volume. When I said 3D volume, I'm referring to the input being in 3 dimensions here, because we have height, width, and now depth, color depth here. This is for a color image here. So our input, go back to it here, is effectively a 3-dimensional input that is fed into here, and these are all in different dimensions as well. So just to effectively go, these are the core layers of a CNN. We have the input layer, our convolutional layer or ReLU layer, pooling, and our fully connected layer here. That's it. Basically, they can get more complex later on, but these are the core layers of a CNN. So why is it called CNN? Well, it's all in the name. The convolutional layer here, that's this one here, and also this one here, comes in sequences as well. You can have, this is how we add depth to a CNN, by having multiple stacked convolutional layers. Now, convolution is what allows it to actually learn image features, and I will explain to you again what image features are, but they're basically what our classifier uses to sort of detect what's in an image. But what exactly is a convolution? Well, let's find out in chapter 7.2. Okay, so in 7.2 we are going to learn what convolutions are and what image features are. So let's begin. So before we dive into convolutions, let's take a look at what image features actually are. So when I say image features, I'm talking about interesting things in an image. It's a kind of a vague term, but it basically encapsulates things like edges, colors, patterns, and shapes. This is a dog here that has been, the edges have been extracted using canny edge detector. So image features are basically just that, just basically one narrow thing that we find interesting in an image. By narrow, I mean like a type of category, like edges or colors. This could have easily been a brown color filter, or blur, or whatever, or pattern, color, or shape. So before CNNs came into the picture, scientists did feature engineering manually. Did you see how I just mentioned that these are edges or color extractors or patterns or shapes? Now what we had data scientists, and I actually had to do this at one time, was extract different features such as histogram of gradients, color histograms, binarization, which means like threshold image, many different things. And it was tedious to actually do this feature engineering, because a lot of times you're just kind of like messing around, trying different things, and you don't even know what works. And in the end, because you don't have a good complicated model that does nonlinear representations well, you still end up getting basically not that great of accuracy. So these are examples of filters learned by this guy here in this publication. This is basically an edge detector here, multiple edge detectors with white and black, like a zebra stripes all over here, different color patterns together. Now, what are these image features here exactly? Like, I'm talking about image features, but what does it have to do with convolutions now? So what are convolutions? Now, a convolution, before I even tell you how it relates to features, convolution is effectively a mathematical term that describes the process of combining two functions to produce a third function. Now that sounds kind of vague until I tell you the third function is a feature map, and a feature map is effectively these things here. So now we imagine we're applying a convolution to an image, so that's applying the process of two functions. So we apply the convolutional to an image to get the feature map. So convolution is the action of using a filter or kernel. We use both interchangeably in this course and in research and theory. So it's applied to the input, and in our case the input being our input image. And the convolutions, this is basically the convolutional process now. Let me just go back to this slide here. So I just want to reiterate that in our case the input, which is the first convolution here, the input is applied to a function called filter or kernel, and that produces a feature map. So the convolutional process is basically executed by sliding the filter, that's a filter or kernel function, over the input image. And this sliding process is basically a simple multiplication, matrix multiplication, or dot product over to produce a third function. So how is it done? So imagine This is basically an input image. This is a 2D, it's not 3D in reality, but this is for explanation purposes, and this is our convolution filter here, just some values in a smaller matrix. And this is our output feature map. So what's going to happen in the convolution process? Well, we're going to basically slide this image here over, let's go back to it here, over this area here, and then again and again, and you'll see it slowly. So when I mean convolve it, convolving means we basically multiply them here. So as you can see, the values were 1, 0, 1, 1, 0, 0, 0, 1, 1, and these values here were 0, 1, 0, 1, 0, blah, blah, blah. I actually didn't use these values, mainly for simplicity purposes, so I changed them to these values here to make this calculation far easier for us. So by multiplying these two together, we get 0 by 1, 1 by 0, 0 by 1, you'll see it here, 1 by 0, 0 by 1, 1 by 0, and so on and so on, and we just add it up and we get 2, and that forms our first output feature in this box here. So how many times can this 3 by 3 matrix be slidden, is that even a word, can be slided over this input image here? So imagine, let's look at it here, we have one box here, then we can shift it again here, 2, just like this here, and then 3 again. So by sliding it over this box, we fill out now a second value in our feature matrix, and I don't have a third one, but imagine it does a third one here, and then starts again at the second row here. So we have 1 here, 2 here, 3 here, and then again 4, 5, 6. All right, so we have basically enough values. So we have for each row 1, 2, 3, and then 3 times it can be slid across here. So we have 9 values in all. So we can actually fill out this entire thing by sliding it across 9 times. That's how we build our features. So by using what I would call a 3 by 3 filter, convolution or kernel, we produce a feature map of 3 by 3 where it produces the filter here. Now, you understand this process. Basically, it's simple math, but what exactly are the effects of doing this? And why is this important? So firstly, depending on the values of the kernel, that was the kernel being this blue box here, the convolution, we produce different feature maps, obviously, because we can have different kernels with different values, and they'll all produce different feature maps. So applying our kernel produces scalar outputs, as we just saw. Convolving with different kernels produces interesting feature maps that can be used to detect different features. This is what makes it important. So imagine we have several filters here, each with different sets of values here, and we're sliding it over here, we're producing different feature maps. So what this means now is that we've now processed the input image into basically features that have been extracted. So let's keep going. So it's important to know the convolution keeps a spatial relationship between pixels by learning image features over the small segments that we pass over. This means that the convolution, even though it's reduced in size here, it still sort of retains some of the spatial information in this larger image, just now it's in a more compressed type form. So these are examples of kernels here. Basically, an identity kernel does nothing. We have edge detection kernels, so simply having these values in this kernel changes an input image into this. It's quite remarkable. But you can actually write some code or try it in OpenCV and see for yourself. You can specify kernels, define your own kernels in OpenCV, and run some convolutions and produce blurs, Gaussian blurs, sharpened images, edge detection. It's actually pretty cool. So let's take a look at an example of a feature applied, or convolution or kernel applied to an image that extracts the features here. So this is an example GIF that I've taken from NYU. You can actually see how when they apply this and slide it across the image here, what the actual convolutional filter output looks like. So this is the edge detector here, and the other edge detector. It's actually pretty cool. Let's look at it again. There. And the other filter. There. Awesome. So now, as you know, that was just one filter. We actually need many filters in our CNNs, at least as within reason. You don't want to do too much, although there's nothing actually wrong with doing too much, just increases your training time and model complexity, and it may be redundant depending on your image dataset. So let's assume we're using 12 filters. How do we actually visualize how that CNN actually looks? So this is it here. So imagine we have an input image that is size 28 by 28 and three dimensions, red, green, and blue. So that's why it has some depth here. And this is our convolutional filter, which is basically this size here, 1 by 1 by 1. That's actually the output, of the convolutional filter for each grid. This is our convolutional filter box here. Alright? So we're actually doing a one-to-one mapping of a convolutional filter. So it's 28, also 28 by 28 by 1. But now we're using 12 filters here. So each yellow block here represents a single convolutional filter, and there are now 12 blocks stacked here. So what happens is that for each filter, we slide it across, fill out our values here, and basically we do that 12 times, and we get our box of convolution, or box of filters here, or feature maps, I should say. This is our box of feature maps. This is our convolution kernel matrix. And in case you're wondering, because it just slipped my mind when I was explaining this to you, because I did this slide a couple weeks before explaining that in this video. Now, you notice that before we had a filter that was size 3 by 3, and we produced a smaller convolution or smaller feature map here. However, in this example, I'm producing basically the same size feature map, and this is actually what we need to do in most cases. We don't have to, but I'll explain to you how we actually end up with the same size image later on. But for now, just assume we run this. Let's say this is a 3 by 3 or 5 by 5 convolution here. We get the output here, and we fill in our feature matrix here, or feature map. So as you can see, this is how our filters look stacked up. You can visually see it quite clear there. So the outputs of our convolutions. From the last slide, we saw that applying 12 filters of size 3 by 3 by 3 to an input image, which was of 28 by 28 by 3, we produced 12 feature maps, so also called activation maps. Now these outputs are stacked together and treated as one big 3D matrix of output size 28 by 28 by 12. And this is now important. Go back to this here. This now forms the input, this big matrix here, into our next layer in the CNN. So now let's talk more about what these feature maps or activation maps actually are and how they represent image features. So now each cell meaning each 1 by 1 point in our activation map matrix is considered basically a feature extractor or a single neuron. And that single neuron is basically looking at a specific region as it slides over the image, or a specific feature, I should say, as it slides over the image. So if we have basically a feature map of say 28 by 28 like we just did, that feature map basically has each neuron, each cell basically activates depending on what it sees in the image. And in the beginning of our neural network, that of our CNN I should say, our convolutional layers basically are low-level feature detectors. And low-level feature detectors are basically looking for simple things in images. Simple things meaning like maybe edges, maybe specific colors, maybe a blob here and there. However, if we have consecutive concatenated convolutional layers, as in deeper networks with rows of convolutional layers, we can start detecting more spatial features like the face of a cat, or the shape of a bicycle, or the shape of a face. So that's how CNNs actually use these convolutional feature maps to detect features. So you've seen so far that we just use a standard arbitrary filter size of 3 by 3, but can we use other sizes, and how do they affect the convolution size and the feature parts of the further parts of the convolutional neural net? So basically that's called tweaking the hyperparameters. So in the next section, that's section 7.3, we look at depth, stride, and padding. Hi, so welcome back to our chapter on depth, stride, and padding. These, I said, were the hyperparameters we use to actually tweak the size of the convolutional filter. So let's take a look and see. So remember, in our previous section, we only used a 3x3 filter or kernel, and that gave us this feature map that was actually smaller than the actual input layer. Now, does it always have to be 3x3? No, clearly not. It doesn't. And that's how we design our feature maps. We tweak some parameters, and these parameters actually allow us to control the size of the feature maps that we produce. So how do we do this? Well, clearly we can easily just adjust the kernel size. So instead of 3x3, we can do 5x5, 7x7. We can change the depth of those filters, and I'll explain to you what depth is just now. We can change the stride and padding. So let's talk about depth first of all. Now, depth is not referring to color depth here where it's 3 RGB colors. Depth refers to the number of filters we use. So remember, in this example here we have one convolutional filter that's being slid across this image, and that produces this one convolutional filter map. Well, we can have as much of these maps as we want. In this example we use 12, but in reality we can use 32, 64, any number of filters. And each filter, during training, actually learns different attributes, different features here that they end up corresponding to different features on this image. And I will explain to you, because right now that sounds a bit vague, like how do these filters actually end up learning different things. It has a lot to do with the random weight initialization and what it picks up during training. It's a bit of a black magic type thing, honestly. However, it actually does make sense when you actually drill down into it. So depth refers to the number of filters being used here. What about stride? Stride is quite simple to understand. Stride is basically the step size we take when we slide these filters across the input image. So let's take a look at what stride actually is. So remember, using a stride of 1, we just take a jump of 1 here and then here again. So as you can see, this convolutional filter or kernel is just being passed one at a time, one cell at a time, and then when it goes to the bottom, it just goes here. So as you can see, this will produce 9 values in our output, and that output is called the feature map. Remember that. What if we use a stride of 2? What's going to happen to our feature map? Let's take a look and see. Stride of 2 takes a big jump here, so we only get 2 values from the top row when before we had 3. Suddenly it's a big jump down here, so we only get 1 here, and then there's going to be 1 more here. So that means using a bigger stride of 2, we only get 4 or 2x2 feature map out of it. Now, is that important? And yes, it is, because think about it now. If you're using very big strides, you're going to end up with very small feature maps, and you don't always want very small feature maps, because then you lose information that's being passed from layer to layer. So this is how we now get into zero padding. Now, zero padding is actually a very simple concept. It refers to a border that we apply to the input volume. And why is this volume needed? Well, as you can see in our first example here, when we use a 3x3 filter and a stride of 1, we ended up with a 3x3 feature map. However, that is still smaller. And imagine we have a very deep network. Well, we haven't discussed very deep networks yet, but imagine we have a next series of convolutional layers after this. Like we use this as the input image now into a next convolutional layer. Right? So what happens in reality is that we have this going to this with a kernel here, then it happens again. Now, as you can see, it's going to get smaller and smaller, and we don't want that. We end up losing too much information, and it ends up being tiny at the end. So this is what zero padding actually does to the input image. It adds a layer of zeros right around it, and what that does is that allows us to actually generate a feature map that is the same size as the input image. So now, if you remember correctly, let's go back to one of my slides. Sorry about all these slides. In this slide here, remember, we passed this kernel across this image, and we ended up with
a filter, a feature map that was exactly the same size as the input image. And I mentioned before that in the previous section that intuitively you know that wasn't supposed to happen, but it did, and I didn't explain how. Now I'm explaining how. It's because zero padding was applied in this example here. So let's move forward to the other slides. Right, so looking at our zero padding example again, we can see how by moving this across, we end up with nice big feature map from the input image. So now we know that we have all of these parameters here. We have the kernel size, the depth, the stride, the padding, and the input image size, and we define these as K, D, S, and P, and I here. Now, this isn't actually calculating our convolutional output per se. Alright, that's actually fairly easy to do if you think about it. We know exactly what the size is, how much zero padding you would need to maintain that image size. However, if you want to make sure those settings that you use here make sense, there's a simple formula here, and it says I minus K plus 2P here over S plus 1. And basically we can use the values in a previous section where we used a 5 by 5 image. So it's going to be 5 minus 3, 3 being the filter size K, plus 2 times 1, 2 being P, which is our padding, as I just said, plus 1. So that gives us a simple thing here, which is 2 plus 2 over 1 plus 1, which is 5. And as long as this formula gives you an integer value, basically you're okay. So let's move on now to ReLU, which is the activation layer of choice for CNN. Okay, so welcome back to our section on ReLU, which is the activation layer of choice for CNNs. So you remember when we talked about activation layers in our neural network section, the purpose of them was to introduce non-linearity to our model. And the convolutional process so far, as you've seen, is completely linear. So we definitely need an activation function to basically add some non-linearity, why is that word so hard to say sometimes, to our convolutional neural network. So let's take a look at what ReLU actually does. So you remember this graph from ReLU? Basically it's a max function, a max zero function. What that means here is that any negative value that is outputted from a node in our convolutional neural nets is basically clamped at 0, and positive values are passed. So applying ReLU to this is a feature map here. So imagine we've come from input image here. Let's imagine it's on the left here. We applied a kernel and we got this feature map out of it. We haven't applied ReLU just yet. So now applying ReLU, this -5 here, and -1 all become 0. So this is what ReLU does to our feature maps. So how does this actually look in an image? This is an example of actually taken from here, that if we have a feature map that looks like this, with black being negative and white being positive, and you only pass the non-negative values, this is what it becomes. So you can see it still preserves a lot of information in this image here, without maybe some of the noise that is seen here. So this is what ReLU actually does. So now let's move on to section 7.5, which is pooling. Hi, and welcome back to 7.5, which is about pooling. This is the next sequence of layers in our CNN. So far, we've dealt with the convolution part and ReLU. Now let's look at pooling, or also known as subsampling. So pooling, as I just said, is also known as subsampling or downsampling, is a simple process where we reduce the size or dimensionality of the feature map. The purpose of this reduction is to reduce the number of parameters that we need to train whilst retaining most of the important features and information in the image. There are basically 3 types of pooling we can apply. There are actually some more, but let's take a look at these 3 main types that are used. So here's an example of max pooling. Imagine this is the ReLU output from this output here was produced from the ReLU layer. So you can imagine these values, these zeros here, were actually negative values. So max pool basically uses a 2x2 kernel here. We can define this kernel size to anything we want, just like we did with the stride of the kernels we used in the convolutional layer. And basically, using a 2x2, it splits this up into 2x2, 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 2x2 grid. So what it does, max pooling, takes a max value out of each, 234, 167, 241, and 235, and puts them into this block here. So this is what we call downsampling or subsampling. Basically, we've sort of like compressed the image here and retained the most max important features. Actually, let's go back to the previous slide and the previous slide. We mentioned average and sum pooling. Now, as you can imagine, average and sum pooling would just simply be the average of these values here, here, or here, or here, and sum pooling would just be the sum of these values here. So that's also a way we can use pooling. However, in majority of convolutional neural nets, we always use max pooling. So this is our layers so far. Just to do a recap, we have our input image with our kernel that is being slid across this image, producing multiple different filters here, all of which are the same size as the input image, and that's because of zero padding. Then we have a real output, which basically is the same size output matrix as this, except all the negative values turn to zeros. And then we have the subsampling or pooling layer or downsampling, which basically reduces this image, this matrix by half, 14 by 14. Because as you can see, using a 2 by 2, we had a 4 by 4. Now we get a 2 by 2, and that's this here. Still 12 filters. However, they've now been downsampled. So let's move on now. So let's talk a bit more about pooling. Typically, pooling is done using 2 by 2 windows with a stride of 2 and no padding applied. That's how we actually get this 4 by 4 here. It takes a 2 by 2 jump, 2 by 2 jump, and blah blah blah. So for smaller input images or larger images, we can use larger pools or smaller pools, whichever you want to do. And using the above settings, pooling has the effect of reducing dimensionality. Width and height, those are the only two dimensions we reduce here, of the previous layer by half, and thus removing 3/4 or 75% of the activation seen in the previous layer. So let's keep moving on. This makes our model more invariant to small or minor transformations or distortions in our input image, since we're now averaging or taking the max output from a small area of an image. What this actually means here is that we're, instead of like looking at specific pixels here in an image, because we're actually doing downsample and looking at the max in an area, we sort of add some sort of invariance or spatial invariance to our filters here. So our filters aren't super specific to certain areas. And remember, they're being slid across the image. So imagine this filter has been slid across the image looking for a specific edge or whatever. It can actually add some invariance now to it. So this actually increases basically the ability of our convolutional model to generalize to information it's never seen before. So now let's move on to what is kind of the final layer. There are some layers in between. I will discuss them later on. But for now, this is the core of the CNN, and this is the last layer, the fully connected or FC layer. Hi, and welcome to chapter 7.6, where I discuss the fully connected layer, and I tell you why it's so important. So the fully connected layer, or FC layer, and it's also called the dense layer in Keras especially, but in a number of documentation and other tutorials, they call it the dense layer too. So previously we saw in our neural net that all layers were fully connected, okay? Now what does fully connected mean? Fully connected means that all nodes in one layer are connected to the outputs of the next layer. Now that doesn't happen in basically throughout the CNN except at the fully connected stage. So the fully connected stage here, basically it's a layer right here that takes the outputs of the pooling layer and then passes it to the fully connected layer here, which then outputs the class probabilities here. So the FC layer outputs these class probabilities, and each one is a probability corresponding to a class. So as you can see, panda, cat, dog. This is clearly a cat. So it does this by using the softmax function. So going back to it here, the FC layer outputs stuff here that goes into a softmax function, and the softmax function basically is what gives it its probabilities, because it must sum to 1, and that's exactly what a softmax function does. Okay, we'll take a look at it here. So by the way, a softmax function is actually an activation function as well, just remember that, and it turns the outputs of the FC layer, the last layer, into probabilities. So let's say the output of the FC layer was 2, 1, 1. Applying the softmax squashes these real value numbers into probabilities that sum to 1, so the output would now be 0.7, 0.2, and 0.1. So now that we've discussed all the building blocks of the CNN, which if we were to go it over now, it would be the convolutional kernel, it would be the ReLU, the pooling, and the fully connected layer with the softmax at the end. So how do we actually train CNNs? We're now about to move on to that section, which is 7.7. Okay, so we've just discussed all the layers that comprise of a basic CNN. So now let's talk about how we actually train our CNNs. So CNNs are basically a type of neural net, and they lend themselves perfectly to image classification. It basically learns spatial image features, but because of the max pooling and multiple filters, it is basically somewhat scale and distortion invariant. So this is an illustration of the feature maps that a CNN learns. Okay, it's taken from this link here. You can check it out. So essentially, you can see the beginning convolutional, or the early. This is input, and this is close to the output, or the output itself. So you can see the early filters learn basically simple, edge detectors or pattern recognizers. However, the mid-level features are a bit more abstract and a bit more complicated. You see these three weird lines here, something that looks like an eyeball. I'm not even sure what it is. Could be a wheel, actually. And then as we go further, the next layer of convolutional filters. Remember I said you can have multiple layers of them, like multiple sequences of convolutional layers? Well, this is exactly an illustration of that. And as you can see, the patterns get much more detailed. And basically, this is how neural nets, or CNNs I should say, this is how their filters actually learn, and this is what they pick up in images. Later on, in about 2 or 3 chapters from now, we're going to do some visualizations of our own. So basically, just a quick review of CNNs again. On our layers, convolution plus ReLU done here, then pooling, then we can do convolution and ReLU again, then more pooling, and then pass everything to the fully connected layer, which outputs our class probabilities. So how do we train CNNs? So just like in neural nets, training CNNs is essentially the same thing, okay? So we have a random weight initialization of the convolutional kernels. That's all our kernels we described before. They basically start with random values. Then we forward propagate an image, one sample image, through our network that goes through all these layers here. And we get the error being basically the class probabilities. So let's say we were looking for an output of 0.2, 0.4, 0.4. When the true probability is with this, basically in class probabilities, you want it to be as close to this as possible, where it's very sure it's in one category and very low probability in the other categories. So then we apply a loss function, pass it through an optimizer, and use backpropagation to update our gradients via gradient descent. And we keep doing this, we keep propagating all our images through our network till we complete an epoch, and then we keep completing epochs until our accuracy and loss are satisfactory. So now let's take a look at how we actually design our own CNNs. Okay, so welcome to chapter 7.8, where we talk about how we design our own CNNs and the layer patterns involved. So basically all basic CNNs, we're not talking about exotic CNNs here, which we will get exposed to later on, follow this sequence. You have an input, a convolution, ReLU applied to the convolution output, pooling applied to the ReLU output, pooling goes to the FC layer, and FC layer with softmax gives us the output. That's basically it. And basically when we talk about deep convolutional neural networks, we talk about multiple convolution ReLU pooling layers. So you can have sequences of 1, 2, 3, these 3 layers, over and over and over again till we get to the FC layer. So here's the basic design rules, okay? Input layers typically are square. So with MNIST 28 by 28 or 64 by 64. Now this isn't necessary, but it simplifies our design and speeds up our matrix calculations. So if you have images of all different sizes, it will be best if you just resize them all to one standard size, okay? Input should be divisible by 4, which allows for downsampling. Okay, that's a max pool layer, in case you forgot, with a stride of 2. So we tend to keep these values here divisible by 4. Filters are typically small, either 3 by 3 or 5 by 5, but they can easily be 7 by 7 or 9 by 9, so don't let me stop you from trying those filter sizes. Stride is typically 1 or 2. I usually use stride of 1. However, if the inputs are large, you can get away with a stride of 2. Zero padding is usually always used so that our convolutional output layers are the same size as the input. And our max pool kernel is typically 2 by 2, which I said previously up here. And dropout, which we will discuss further, is a very, very useful technique and easy to apply to avoid overfitting in CNNs. So, part 2 of this slide. So the more hidden layers, the more features, okay? That makes sense because obviously each time you do a convolution, apply a convolution kernel, you're getting a bunch of filters, which obviously means more features. So we want, if our data set is complicated, we want to have maybe at least 2 or 3 sequences of convolutional layers. That means this here, these two, ReLU, convolution, boolean, at least 3, maybe 2. And that way, this is the sequence here, input conv ReLU pool again. And basically this allows our filters to learn low-level features here, then mid-level or higher-level features here. So basically, this is some examples of CNNs we'll be actually building in our course. This is AlexNet, which is one of the early, most famous CNNs here. This is an example of how it's constructed. You can take a look of it here. The parameters they used. Stride of 4, interesting. So you can take a look. Alright, as you see here, there are actually 2 fully connected layers, and you can actually do that to basically, you can have consecutive dense layers of fully connected layers, and it doesn't even have to have the same number of values, okay? It's another one we'll be making in this course. We will be making it and using it, the pre-trained model. We aren't going to train VGG or VGG19. It is insanely parameter intensive, and basically, I mean like thousands and millions of parameters, and it takes a while to train. Okay, so now you're ready to actually start building convolutional neural nets in Keras. This is the exciting part of the course, and it's actually quite easy, so let's get down to it. Hi, and welcome to chapter 8, where we actually get to build a CNN in Keras. So this is going to be an exciting chapter, and here's what we're going to learn. Firstly, brief introduction to Keras and TensorFlow, what they are and how we use them. How we start building our handwriting recognition, basically our approach to this problem, how we load our data, how we get our data in the right shape or format for Keras, what is Hot1 encoding, how we build and compile our model, how we train our classifier, how we plot our loss and accuracy charts that we've seen before, how we save and load our model, so after we train it, we can now save it and reuse it anytime we want, how to display basically our model visually, so it's like an architect blueprint of our model, and basically how we actually can now build another image classifier using the CIFAR10 dataset. So let's get started. Hi, so welcome back to chapter 8.1, where I introduce you to Keras and TensorFlow. So what exactly is Keras? I've mentioned it countless times on this course, but I haven't actually told you precisely what it is. So Keras is a high-level neural network API for Python, and it makes constructing neural networks, all types, not just CNNs, but all types of neural networks. It makes it extremely easy and extremely modular, just to add layers, swap in stuff, change different things, configure your loss functions, configure your different types of activation functions. It's quite nice. It has the ability to use TensorFlow, CNTK, which is used for natural language processing, and Theano, which I used to use quite a bit of Theano. However, I've now moved to TensorFlow and I haven't looked back. Not because Theano is bad. Theano just basically has stopped being updated now. Project is pretty much done and closed, and everyone is pretty much adopting TensorFlow now. And it was developed by Francois Cholet, and this has been a tremendous success in making deep learning much more accessible to the masses. So what is TensorFlow though? I said Keras used a TensorFlow backend, but what exactly is a backend? Okay, so TensorFlow is an open source library that was created by the Google Brain team in 2015. Probably was being used inside of Google internally for many years prior to 2015. And basically it's an extremely powerful, extremely efficient and fast machine learning framework that is used for high performance numerical computation across a variety of platforms such as CPUs, GPUs and TPUs. It basically, these engineers, these guys at Google Brain, they developed this basically super fast library similar to NumPy, but basically incorporated it and built it around deep learning. So they have all these deep learning functions that are part of the TensorFlow framework. It too actually has a Python API, and it pretty much is accessible and easy to use, but Keras is much easier to use. So why use Keras instead of pure TensorFlow? As I said, Keras is extremely easy to use as it follows basically a Pythonic style of coding, and it is extremely modular. You don't even have to be a proficient programmer to use Keras. This modularity means that we can actually just start doing different things with our neural nets or CNNs. Can easily change cost functions, optimizers, initialization schemes, activation functions, try different regularization schemes, introduce more layers, reduce number of filters. All of those things are done super easily inside of Keras. So it allows us to build these powerful neural nets quickly and efficiently. And obviously it works in Python, and Python is one of my favorite, actually it is my favorite programming language ever, because it makes so many complicated things super easy. TensorFlow is definitely not as user-friendly and modular as Keras. I've used TensorFlow a bit, to be fair, but I was using Tiano at that point, and Tiano actually was quite hard, so TensorFlow seemed easy for me at that point. However, nothing beats Keras in terms of ease of use. So unless you're doing complicated models or academic research, or basically working for some sort of high-performance startup, you don't necessarily need to use pure TensorFlow for anything. So now you're ready to see some actual Keras code. Well, it's actually Python code, but we're using the Keras library. And this is how we actually construct and build models inside of Python. So firstly, we import the sequential model from Keras. Basically, the sequential model is the main type of model you'll be building in Keras. Basically, all the CNNs and neural nets I've shown you before were sequential models. If you're doing something exotic, then it will probably not be sequential, but that is rare and probably beyond the scope of this course right now. It's basically academic research. So let's move on. So we defined our model here. We initialize it by running this line here, sequential, these two brackets. And then now let's add some convolutional layers to it. So before we do that, we have to import these layers from Keras here. So from keras.layers, we import dense, dropout, flatten, conv2d, max pooling. Now I don't have dropout here, but it's being used in the model we actually are going to code. So I left it in just so you guys know how it's referred to here. Okay. So firstly, model.add. We're adding our first layer here. So our first layer is a conv2d. That's what we call it. And now we have open brackets here, and we have some parameters to fill out. So let's go through these parameters. First one is a number 32, then the kernel size we can see here, then the type of activation we use, and input shape being equal to input shape. That's a bit confusing. I'll explain that to you shortly. So let's go through each one. First one here, 32, that specifying firstly the number of kernels or filters. So in our first layer, we're using 32 filters of kernel size 3 by 3 with an activation function using ReLU, and our input shape is equal to input shape, and that's because previously above this code we created an input shape parameter, a variable I should say, that was 28 by 28 by 1. That's our input shape we use. So I just left it out here for convenience, because we tend to leave it out and just have it defined outside of the scope of this declaration here. Now to add another layer, it's as simple as model.add. Keras is so easy to use. You just keep using model.add, and it stacks these layers on top of each other, starting with the first to the bottom layers. So now we add another convolutional layer, 64 filters this time, same kernel size, and note we don't need to specify kernel size every time we do it. It knows that the second parameter is kernel size, so it's 3 by 3, and again, activation, ReLU. And now, you've noticed, we don't need to specify an input shape here. And do you know why? That's because this layer is directly connected to this layer. So it takes the output of this layer and it knows the output. So the output of this layer is effectively the input into this layer. So we no longer have to declare inputs anymore. So now you can add a max pooling, and I said before we're going to use a max pooling of 2 by 2. So that's simple here. We have model.add max pooling 2D and specify the pool size. Open brackets 2 by 2, close brackets for this here, close brackets for this here. And then we do a flatten. I haven't discussed flatten. Flatten is an actual layer. It's basically a function we do that we use to feed the dense layer or the fully connected layer. You'll see it visually in the next diagram on the following slide. Basically we then add a dense layer here with 128 units all being activated by ReLU, and this is connected to another dense layer here which outputs the number of classes. So classes in this dataset here were 10 because we're using the MNIST dataset 0 to 9, and we use the softmax activation to get basically the probabilities. So I hope you think this is quite simple, because to me this is quite basic. You may take a little while just to get familiar with how these things work, but you'll get used to it in this course, I guarantee it. So let's take a look at what we've built here. Okay, so this is actually what we have built so far. So we have our input image here, 28 by 28 by 1 because it's grayscale. If it was a color image, or RGB image, it would be 3 depth here. So as you saw before, we have 32 filters here connected to another conv layer with 64 filters here. And you may have noticed the size of the image shrank here. It became 26 by 26 and then 24 by 24, and that's because we didn't use any zero padding. And I'll show you guys later on in code how to do zero padding. It's quite simple, but for now just remember, when you don't use zero padding, our input image, our convolutional feature map size reduces from the input image size. So we have these two conv layers stacked here. Then we have our max pooling, which basically shrinks this by half. I have a dropout thing here, but we didn't actually use dropout before in the code. But in the actual code when we start our project, I'll show you quickly how to actually implement dropout. It's one line, super easy. What I wanted to show you though was we have the flattened layer here. Now the flattened layer, if you go back to it here, we just flatten in brackets. And what does that actually do? Flatten basically takes this multi-dimensional matrix, 64 by 12 by 12, and basically turns it into a row of 9,216 columns. So what this means here is that we just flattened this matrix. So instead of having 12 by 12 by 64, imagine you just built an entire long row where it's the first 12 here, then second 12, and then it's just consecutive long, basically a long row. And that becomes this output box here. And now this output box here is fed into the fully connected layer here with 128 nodes. Let's go back to it here. So we defined it here, and each node is connected to a ReLU activation unit. And then finally, we connect this to our final dense layer with a softmax activation function, and it outputs to 10 nodes. 10 nodes because our MNIST dataset has 10 classes. So that's how we get our probabilities here. So it's not illustrated here, but later on you will see it. So now that we've built our model, we are ready to compile this model. So compiling simply creates an object that stores our model we've just created. And we can specify our loss algorithm, our optimizer, define our performance metric that we want to look at. And additionally, we can specify parameters for the optimizer, such as learning rates and momentum. So this is a simple modeler compile code here. We have our categorical cross entropy defined as a loss type. We have our optimizer, SGD, being stochastic gradient descent. And we have our metrics to look at, being defined as accuracy. So how do we fit or train our model now? So following a simple, basically what sklearn, which is the most established and popular machine learning library on Python prior to TensorFlow and Keras. Basically they just applied model.fit, where they use the training data, the training labels, xtrain and ytrain. That's what they are. You'll see them referred to in the code soon. Specified number of epochs and the batch size. Now the batch size, this doesn't impact your learning that much significantly. However, you basically should use a largest batch size as possible that your memory allows. So you can experiment and try it. You will note if you try a too large a batch size, your kernel will crash. So generally I tend to not avoid having my kernel IPython notebook crash. So I'll use basically a batch size of 32 for pretty much small images or 16 for larger images. And once we do that, we can now evaluate and generate predictions afterward. So by running model.evaluate and feeding it the x-test and y-test labels with a batch size, we can get these metrics here, this metrics parameter, this metrics object. And then we can use that to actually look at different graphs and different interesting performance information from our model. And if we wanted to have a predict an individual point, like you have an image and you want to get the actual class it belongs to, you can use model.predict. Model.predict allows us to feed one image at a time, or you can feed the entire data set here as well. So that's it. So now let's get started to build our own MNIST handwritten digit classifier. Hi, and welcome to chapter 8.2. We are now about ready to start building our handwriting recognition CNN in Keras. But before we actually dive into the code, let's actually talk about how we approach this problem and what the problem actually is. It's a very good practice in data science to actually think about your problem, think about your data set, know a bit about your data set first before trying anything crazy and training a model on your data. So we're going to use the MNIST. This is a famous data set. Basically, it comprises of 60,000 images with 10,000 test images. And 60,000 images are comprised basically of 10 classes. So you have like thousands of like zeros, ones, twos, all of them here in this training data set. And you can read more about it here. You can click these links afterward. Basically, this is the guy, Jan LeCun. Basically, he was a guy who trained LeNet, I believe, and that was basically the famous CNN. It actually scored 99% accuracy on the MNIST dataset. It's quite interesting. So the problem. Let's look at the origin of the MNIST dataset. It was developed by the US Postal Service because they needed a way to automatically read postcodes, handwritten postcodes on mail. So the aim of our classifier now is to take these digits and basically build a model that will tell us this is a 5, 6, 2, 7, 4, and 8. And this is the CNN. Remember we had outlined the CNN before, and I showed you how to build it in Keras. We're actually now about to build the CNN in Keras. So it's going to be quite exciting. So let's move on to our IPython notebook. Okay, so before we actually dive into our notebook, I'm just going to talk a bit about loading our data. So Keras has some built-in data loaders that are quite easy to use. However, we still have to do some manipulation to our data afterward, and we'll get into that shortly. But let me just show you quickly what this is. So from Keras.datasets, we import MNIST. There are a few datasets Keras can automatically import. MNIST is one of them, and Sapphire 10 is the other. So this is how the dataset from the load function comes out in this form, and we can define these variables as any names we want. However, this is a standard naming convention I like to use. I realize that Francois Cholet actually uses these same variables names as well, and in a lot of tutorials you'll see sometimes slightly different naming conventions, but generally xtrain and xtest are basically the training data and our test data, and ytrain, y refers to the class labels. So we have ytrain tied to xtrain. This is going to be the same length. So if this is like 60,000, this will be 60,000. And if this is 10,000, this will be 10,000. 10,000 like records, I mean. This is obviously an image here and an image here. So it's going to be slightly different shape. So we can actually print a shape here, xtrain.shape, and it gives you this output here. So it tells you that we have 60,000 images, and each image is of 28 by 28 dimensions. So let's do this now in our IPython notebook. Alright, so this is our IPython notebook here, 8.3 to 8.10. It's in one notebook. It's in our same deep learning folder you've seen before. So this is the code I just showed you in the previous slide. So let's just go ahead and run this code by pressing Shift Enter. And it takes a little while to load. If you don't have the data saved on your machine, you'll see it downloading. Some download bars come up here below. So we just printed the shape for ytrain. Let's take a look at xtrain. Xtrain is what we saw in the previous slide, 60,000 by 28 by 28. And let's see what ytrain looks like. I think we just looked at it, 60,000. Let's see what xtest looks like, 10,000 by 28 by 28. And this, we assume, is going to be 10,000. Good. So I just did it here, but initially we can always do it here. So in this step 2a, we examine the size and image dimensions. It's not required, but it's a good practice, just to check and make sure all your data is correct. So we know our data consists of 60,000 samples of training data and 10,000 of test data. And our labels are appropriately sized, so we actually should check this here. Appropriately sized meaning that they're in the correct format that Keras requires. And as I mentioned before, they're 28 by 28, and there's no third dimension or fourth dimension if you want to consider this being the first dimension here, this meaning the number of images stored here. So let's take a look at what happens when we run this code. It prints out this here, which is the shape we saw before, how many samples in our training data, how many labels are in our training data, how many samples in our test data, and samples and labels in our test data here as well. So these all match up, that's good. And the dimensions here are 28 by 28, 28 by 28, so everything is all good. You can take a look at this code and try to understand it if you want to. It's quite basic and simple. Basically we use, these are all NumPy arrays when it's loaded into it here. And basically we can use the dot shape function, which is an extremely useful function to just get a shape, basically the dimensions of your data array. So now let's visualize some of this information. So I'm going to do this in two different ways, okay? I'm going to do this with OpenCV, then I'm going to do this with Matplotlib, and you can use either one going forward. I tend to use Matplotlib if I'm plotting multiple images on the IPython notebook, and OpenCV if I'm testing and wanting to display text over an image. So let's try this. There we go. It pops up in the window here. So we took a look at it's a 9 again, 3, 2, 0, 1. So we just brought up all these windows here and all of these digits. These are random digits. We use this function np_random, and this defines any random number between 0 and the whole length of our training data. The length of our training data, if you remember, was 60,000. So this generates a number from 0 to 60,000 and displays the image here using our OpenCV functions. So let's now do the same with Matplotlib. This is the code to basically plot it in Matplotlib. This is not the actual most efficient way to do it. The most efficient way would be doing it into a loop, but I just left it here for you so you get an idea of how we use subplots to plot it. So let's do it. This is good. X-ray is not defined, and that's because this one may have changed it before, but let's run it again. There's another X train right here. There we go. So I've just plotted 6 images in a nice small grid here. So this is why I said I use Matplotlib to display images in the IPython notebook. I find it easier and nicer to work with. So that's how we basically import our data set and visualize some data from our data set. Next, we're going to prepare our data set for training. So let's take a look at that shortly. Right, so we've just imported the data into Keras. However, that data is not in the ideal or the correct format that Keras needs to train on. So this chapter is going to be a tiny chapter on how to get this data into the correct shape. So let's look at the next slide. So as I said before, we've brought this in here and imported it here. All right. However, Keras requires it to be in a special shape, and that shape basically is number of rows, columns, number of samples, rows, columns, and depth. So this is how Xtrain looks here, but how Keras actually wants it is 60,000, 28, 28, and 1. So we sort of have to add a 4th dimension onto our data, and that's how we do it here. So now let's do this, and the reason Keras is looking for 4th dimension here is because when you load a grayscale image dataset, it doesn't add the dimension of the depth, the color depth, mainly because it's a grayscale and there's no color depth. If it was a color image dataset, you would have the tree popping up at the end here. However, we need to add this 1 just to indicate to Keras that it's a grayscale image dataset. Otherwise, it's going to return an error saying it's in an incorrect format. So to change this, you just use NumPy's reshape function, which is quite simple to use. You just use xtrain.reshape, take the first 60,000 digits here. That's when you use xshape. This is the first dimension that 0 addresses. Then you enter 28, 28, or image rows, image columns, and add the 1. And it's quite simple to use. So let's return to our IPython notebook now. Okay, so like we just saw, this is a section of code where we reshape and add the 4-dimension onto these training datasets and test datasets. I didn't point this out to you before, but we just get image rows and image columns by simply just addressing the first dimension of the shape here, xtrain. Now we use xtrain 0 and xtrain 1. We don't need to use xtrain, we can use xtest as well, because they're the same dimensionality. However, this just gives us the rows and columns. So let's actually print this out so you can actually see what's going on here. So let's run print that. You'll see it returns 28. So this is getting the 28 here. And if we were to just use this for columns too, you'll see we'll also get 28. Alright, so moving on, this is fairly simple for you guys. Let's make our code nice and neat again. This is how we make the input shape. Now you've seen before we needed the input shape dimension in the first layer of the convolutional neural net. And this is how we just create our image shape here. It's a tuple that's combined with rows, columns, and the dimensionality of the depth of the image. This would be 3 again if it was a color image dataset. And because Keras expects data to be in a float 32, right now I believe it's going to be in some sort of integer format here. So we just need to change this. So we just change xtrain as type float 32 and do it for xtest as well. We don't need to do this for the labels, just the training data. And this is how we normalize our data. We normalize our data by dividing it by 255, because remember our images range from 0 to 255. So if we divide our image data by 255, we basically bring it into range 0 to 1. So that's quite simple here now. And basically we just print this out again. You don't need to do this because we did it before, but just to do a sanity check on our data. So let's run this again. If you want to see what xtrain actually looks like now, this is it. You can see basically the decimal points because it's kind of hidden here, but all the data ranges from 0 to 256, to even 0 to 1 right now. Okay, so let's move on to hot encoding our labels. Hi guys, and welcome to chapter 8.5, where we talk about hot one encoding. So as we saw before, we did some transformations on the xtrain and xtest data. That's our image data. Now what about our label data? That's ytrain and ytest. Well, let's find out. So let's recap what we did on the image data. We added a 4-dimension to go from this to this. We changed it to float 32 data type, and we normalized it between 0 and 1 by dividing by 255. But what do we do to the label data now? Let's check. So the label data is basically in this form. For ytrain, it's going to be a matrix that is 60,000, that has 60,000 elements, and each element indicates a class label. So for ytrain, which is a 28, the first element in xtrain is going to be 28 by 28, and this 0 corresponds to its label here. However, Keras does not use label data like this. It needs it to be hot one encoded. And what does that look like? That looks like this. So we have labels here, and instead of having a 4 being represented here, it's basically a matrix that has 10 columns now. So instead of having no columns, so effectively one column, sorry, 60,000 columns, it has 10 columns here and 60,000 rows. And each column, each row, sorry, has basically a 1 or a 0 indicating which label it is. So imagine we have this being transformed. Sorry, let's look at this. This is the third row here being transformed into this. So instead of having this row be 4, hot one encoding makes it into this. I hope you understand clearly. So we're going to do this now in our IPython notebook. Okay, so step 3b is the hot one encoding of our Y labels. And to do this, we basically use NP utilities that are imported from Keras utilities. And all this does here is just sends it to categorical. That is how Keras calls this function, hot one encoding, to categorical. So we have ytrain is equal to NP utilities dot to categorical, and you just put the ytrain here, and that transforms it. So let's take a look at how this actually looks. So let's run this here. So now ytrain, let's look at the first row in ytrain. It's this. And basically you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. And with this one, this looks like the 9, 8, 7, 5th element here. So this is number 5. So the first element in our training data is number 5. So now let's move on to creating our model. So now we move on to a simple step where we actually build and compile our model in Keras. And this is the model we're going to build. As you remembered, I've shown you this before, how you actually add layers, how we actually do max pooling, flatten, dense classes and stuff. This is actually quite a little useful diagram I created that shows you how to basically layer and add each piece here, including dropout and including our flattened layer here as well. So let's go ahead in Keras and run this and compile our model. Okay, so welcome back to our IPython notebook. So I'm pretty sure this code looks familiar because you would have seen it in the presentation slides earlier. So remember I said we're building a simple convolutional neural net? This is how we do it. We have 32 filters in our conv layer, kernel size 3 by 3, activation ReLU. We have the input shape, which we defined above here. Actually, it was in this block right here. And then moving on, we have another convolutional layer with same kernel size, same activation. We have the max pooling downsampling layer. We now use dropout, and dropout is simple to implement. You just model add dropout and specify p. We use p as 0.25 here. We then flatten this layer, have a fully connected dense layer with 128 nodes with ReLU. We add another layer of dropout, and we have a higher dropout here. Note you can play with these values and see what gives you the best. You tend to start with dropout smaller on top and get larger, but you don't ever really go larger than 0.5. And then this is our last dense layer, which is connected to 10 nodes, which is our number of classes. And our number of classes was defined right here. That's basically the length, number of columns I should say, in this array. And that's it. So I talked about compiling a model. Now when we do model.compile, basically we're taking these layers, creating a model, and then specifying what type of loss we're using, what type of optimizer we're using, and the metrics we need to look at. And these metrics we need to look at are basically the metrics that will be output when we started to train our model, when we start training our model. And by doing model print here, we can print the model summary and take a look. So let's check it out. This is very cool here. Let's go through this quickly. So when we print a model, we actually see each layer we have. This is each layer we specified above here. And what's cool about this is that it gives you the output shape. So we know the input shape coming into this here. The input shape was 28 by 28 and dimensionality 1. And we have 32 filters here. So our output shape, if you remember correctly, is going to be 26, 26, 32, with 32 being number of filters. And these are the number of parameters in this layer here. So this is pretty cool. So now we have second convolutional layer here. Same thing again, but now a lot more parameters going forward. We have our max pooling here, which is just process, no parameters. Dropout again, flatten again, and flatten has an output shape of this, as you can see. It's just this expanded into this. We have our fully connected dense layer here, and this is where the bulk of our parameters actually exist. And we have dropout again, and then our fully dense connected to the 10 classes here. So this gives us our total number of parameters, total number of trainable parameters. We have 0 non-trainable parameters, and we will come to what non-trainable parameters are later on. And so we're now ready to train our model, so let's get to it. Okay, so welcome to 8.7, where we start training our classifier. So let's return to our IPython notebook now and get started at actually in doing some training. Okay, so welcome back to our IPython notebook, where we're going to start training our model. So let's go through this line by line, alright? So remember batch size, which is basically how many images we process in one batch. Effectively, this depends on how much RAM or VRAM you have available. Because MNIST is a small data set, you can probably even get away with going up to 128. However, let's put it at 32 to be safe, in case you have lower specs on your system. For epochs, usually we can use 10 or 25 even, but for this demo, let's just use 1 so you can actually see it run and actually see what happens at the end. So now let's talk about model.fit, and you have something called history equal model.fit. Now ignore history for a second. The key part here is model.fit. You don't actually need this history stuff here. This history is mainly needed to plot our graphs afterward. But for now, you can train a model without doing this. You can simply run this line and it trains. So let's look at what inputs we need into model.fit. We need the training data. We need the training labels in the format we specified above. We need to specify our batch size, which is 32, epochs, which would be 1, verbose. Basically, that just tells us how much information we want to see while we're training. I recommend verbose 1 because it's nice to look at and provides a lot of information. And lastly, the validation data, which would be x test and y test. And this is also paired in a tuple. As you can see, these brackets basically ensure it's a tuple. And that's what we fit our model on. And lastly, let's take a look at this line. This is where we get our evaluation metrics at the end of our training. Evaluate basically just gives us a score at the end, a loss score, and accuracy score. So let's now run this and visualize how training is done. Amazing. So now, I find this quite interesting to watch, but you may be bored. But right now, this is basically going through the images here. How many images are we've trained so far in this data set? The estimated time to completion, 2.5 minutes left. Our loss, and you can see it continuously going down slowly. Actually, this is pretty fast, to be fair. And our accuracy. This is a part I like to watch too as well. Our accuracy is slowly going up the more and more data we feed our model. And this is on 1 epoch, and we're already at 60% accuracy. So if you wait this out, I'm going to fast forward the video while we watch this. You can actually see after 1 epoch, we actually reach quite good validation and training accuracy. However, you don't see the validation accuracy and validation loss just yet, because right now what's happening is that we're passing our dataset, our training dataset, to our model and back propagating it and updating the weights. And that is how these things are improving. Loss is going down, accuracy going up. And once 1 epoch is complete, then we pass our test data into it, and then we see our validation loss or test loss, and our validation accuracy or test accuracy. So let's wait until it's done. Okay, good. There we go. We're finished. So now let's look at the results here and try to figure out how we analyze what had just happened. So as you can see, after we fed all 60,000 images into our model and trained it, updated the weights, we now have a loss that is decently low, 0.59. We have our accuracy on our training data set that's at 0.8145, that's 81.5% roughly. But interestingly, our validation loss is even much lower than our training loss, and our validation accuracy is 93%. Now that's not normal, but it's a good problem to have. It means that our model has generalized very well and is actually quite accurate on our test data. Now this doesn't always happen. Usually you'll always, or in most cases, have a higher accuracy in training than on the validation set. However, we wouldn't complain about this. This is a good problem to have. And basically we have our loss and test accuracy printed at the summary here. It's also the same values here, but we just run this again just to basically see it at the end. If you have many epochs as well, this is a summary at the end of the model. Okay, so now we're going to move on to plotting our loss and accuracy charts. Basically what you should do is run this for maybe 10 epochs so you can actually have nice graphs. Okay, so now that we've trained our model for maybe at least 10 epochs, we can start plotting our loss and accuracy charts. And I don't know if you remember those charts correctly, but let me show you what they looked like in our previous slides before. This is an example, this is not real data, of overfitting on our charts. So as you can see, this was basically, we got very bad test loss and test accuracy, but really good training accuracy and very low training loss. Okay, so let's see how we actually plot these graphs in our own IPython notebook. Okay, so here we have the training output of 10 epochs. As you can see, it starts at 1, goes all the way to 10. And as you can see, the training accuracy starts at 91, then gets better and better, And look at evaluation accuracy. It's basically a little hard to see because it's all the way here. But it starts at 95, and then 97, 97.8, keep going up and up to reach 98, 98.6. So that's pretty good. But it would be nice if we had all of these data on a graph, wouldn't it? So this code, it's pretty simple matplotlib code, will actually go ahead and process these plots for you. So let's print them. This one is our loss chart. So this is pretty nice. We can see our validation and test loss here. Starts at somewhere high, 0.14 roughly, and goes down all the way to maybe 0.3 or 0.04 actually, sorry. And this is a training loss here. So you can see this as well. So it's very nice visuals, and when you want to just see if things are overfitting as well, you can actually start seeing things like the training loss, the training accuracy basically getting higher, but validation loss or validation accuracy getting lower or worse. So let's look at the accuracy plots now. This one plots the accuracy here. And basically, actually, I mentioned before how we equate the model stuff to history here. History basically allows us to store this data here. So then we can actually refer to get our history. So history.history creates a history dictionary, and then we just get a loss from this dictionary, get a validation loss as well, and we just equate them here, and this gives us an array of those values, and then we can plot them here and tweak things like line markers, line size, and we do the same for this here. We actually, instead of getting loss, we get accuracy now. And as you can see, this is a nice chart. Always good to see both of these things going up and up. What's good about this, at least not always, this doesn't always happen, but what's good is that validation accuracy is higher than training accuracy. So that means it's generalizing quite well. So you want to see these both move in the right direction. You don't want to see the blue peak and then come down, and you don't want to see this going up and up while that happens, because that means it's overfitting. Okay, so let's talk about how we save our models that we just trained. We spent some time training a model, and we don't want to lose this model when we close our IPython notebook. So let's figure out how we save and load our models. Okay, so we just spent so much time training our model, so let's get to saving it now. So if you scroll down below these charts here, the code to save is actually quite simple. It actually is part of the model object, and you just specify the directory and file name that you want. So basically we can just call this chapter 8, which is from 8 here, mnis simple CNN 10 epochs. You can actually put an underscore here, make it look a little bit nicer, and voila, it's saved instantly. So now, if we want to reload our model, let's just enter a new file name here. And we use Keras's load model, which is part of the models library here. And this is what's strange to most people. Loading isn't as instantaneous as saving. And that's because it has to actually unpack everything now and put it back into the model format. It's a bit tricky to understand. I actually spent some time trying to figure it out because I had a project where I was loading 50 different models at once, and it was taking maybe about 5-10 minutes to load all of them together. So let's just run this quickly, and there we go. This took about 5-10 seconds, and so now our model, which was called the model before, is called Classifier, and now we can use it here, Classifier, just like we were using model before. They're interchangeable now because our model is effectively our classifier. It's just a different name. What I mean by that is, you see how we declared this as model equals sequential? Now that we've reloaded our model, I didn't want to overwrite what we had saved before as a model. So effectively model is now, as we've saved it and loaded it, it's now effectively a classifier. Or called classifier, I should say. And we can load it here and basically run some tests. This has an error in it here. Let me just delete this quickly. And this should work fine now. There we go. So we're actually running some tests on our models here. So this is a 0, this is a 3, 8. You can see how accurate our new MNIST model is. It's quite cool. And this actually looks like an N, but it's actually a 7 because it's a bit tilted. So that's good. That's great, actually. We've just loaded and trained and tested and plotted and analyzed and done all of these things for our first model. So if you wanted to put it all together, because you don't actually need to have every block separate like this, this was basically for teaching purposes. I actually never separate out these things that much. But let's put it all together. So quickly you can see this is everything here. And you run this and you basically start training instantaneously here. Hi, and welcome to chapter 8.10, where we're actually going to use Keras to display a visual output of our model. So remember before previously I was drawing out this nice visualization of our model. Well, Keras can actually do something not quite as nice as this, but it produces a pretty decent model visualization that helps you basically show people and explain your model. So let's see how we do it. Let's go back to our IPython notebook. Okay, so now we're about to visualize our model. So to visualize our model, we need to import this library from Keras here, this function. It's called plot model and it's found in Keras utilities.visualization utilities. So viz_utils for short. So what we do, we recreate our model first. We don't necessarily have to do this, but it's good practice just in case we didn't do it before in the previous layers, in the previous cells in this IPython notebook. So let's go ahead and run this line, run this block, and we get this table, which is our same model output from before. All right. This in itself is a pretty decent visualization. However, it's not like a visual diagram. What we're going to do is produce a visual diagram now. So to do this, we use the plot model function. And the plot model function basically takes a model that we defined up here. We enter a path for the file to be saved. So we just use this path here, which is where our trained models are saved, and we give it a file name, model_plot.png. We can be more descriptive and give it like mnist model. All right. And then after we use matplotlib to actually show, so we just point matplotlib here to the image directory of where we saved it, and we plot it here, and it comes up below right here. So let's see how this works. Let's run this block, and there we go. Here's a nice model visualization. What's cool about this is that we have the inputs and outputs coming in and out. So this is actually quite nice. This is basically a random number. I've never been able to figure out what this number actually is, so pretty much ignore it for now. But what's cool is that we actually have our layers coming in here. We have our conv layers, there's 2 layers here. Our max pooling, it shows input outputs. What dropout doesn't change anything, just drops out some layers while training. Flatten, which we know what it does now. Our dense connections here, our dropout again, and our fully connected layer at the end here, which is also a fully connected layer here. And basically this is it. So if you were to go to this directory here, let's go to our deep learning directory, and let's go to our train models, we can see, here it is. And it's clearer and sharper than in the IPython notebook, being a PNG file. And that's it. So we've just successfully saved. Okay, so you've just finished looking at your MNIST dataset, your first MNIST model. So basically you've imported the data, you've created your model, you've trained it, and then if you've analyzed the results, you've saved it, you've loaded it, and you've tested it on some real data. So now let's do the same for Sapphire 10. We're not going to break it down into all the steps together. I'm actually going to show you now how we actually just do it all in one sequence of code, similarly to what we did at the end of the MNIST chapter, but now for a different data set. So let's get to it. But first, let's talk a bit about Sapphire 10. Sapphire 10, basically it's a huge image data set. I think it's about 60,000 images as well, or maybe more. And basically it has 10 classes here. Airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. These are some sample images in it. And we're going to train a classifier that actually detects what is seen in an image. So if you show it a picture of a car, should know it's a car. A dog, should know it's a dog. And for the other categories here. So let's get to it. Okay, so opening our 8.11, building a CNN for image classification, Sapphire 10. That's the file name in our notebook folder here. Basically, I just define the categories again, and now we get straight to it. Let's just go through this quickly. We have all our imports here, probably some that aren't even necessary. I tend to do that sometimes when I'm testing stuff. My boss gets irritated with me quite a bit for that, but fair enough. I still do it from time to time. We have our batch size, we have a number of classes, we have epochs. We load our dataset in right here, which we imported from here as well. We just display our shapes just to get a handle on what we're doing with our data. It's always a good idea to see to just quantify how many datasets, like how big is your dataset, what's the shape, what's the size of our test dataset as well. So then we just do a quick formatting here. Because Sapphire 10 is 3 dimensions, we don't actually have to add a dimension onto it. It just comes up automatically here. Then we just change it to float. We divide by 255. And we change the test labels and the training labels to categorical or hot one encoding it. We define our model here, which is basically This should be the same model as we did before, but I think I've added in, yep, I did. I added in 2 more convolution layers here. Also, what's different about this model is that we have 32 filters and 32 filters here for the first 2 convolutional layers. Then we have the activation defined outside of it. I actually have did that on purpose, because I remember when I was creating this table, this model, I actually wanted to show you there's a variety of ways to actually create these models. This isn't meant to confuse you. This is meant to actually show you that Keras is very flexible. And you will find a lot of example Keras code where sometimes people define the activation layers outside of the conv layer here, and sometimes just add it in here. You can easily have just gone and put activation equal relu here as well. So going back to this, we have conv, our second conv here, relu, max pooling, dropout, and we have 2 more convolution layers here, each with 64 filters and activations relu, max pooling and dropout here again. Then we flatten everything, and now we have a much larger dense layer here. This outputs, this basically connects to 512 nodes, and then it goes to relu again, and then we have it connected here to this number of classes, which is 10, which we defined above, and we use a different optimizer, RMS prop, and it's defined outside here. We compile our model and print it. So let's print this and see how it looks. Very nice. And as you can see, even though this model is more complicated, the number of parameters doesn't increase that much, which is good to know. It's always good to know to check number of parameters in your model, because the more parameters there are, usually the longer it takes to train. And you can train your model here. Let me just rename this so I don't delete the previous model I trained. And basically run this. I'm going to run this now. There we go. So as you can see, because the images are bigger, even though this data set, as you saw here, is only 50,000, I said 60,000 before, but that's because I added the test and training. So we're training on 50,000 images here, and it's honestly not going that slow for CPU training. We're going to do maybe about 10 epochs here, I believe I set it at, well, 1 epoch actually, just for experimental purposes. And you're already seeing that basically an untrained classifier, basically guessing, would give you 10% accuracy, 1 in 10 chance, and we're already close to 1 in 2 chance, sorry, 20% accuracy, 1 in 5 chance of getting it right on a training data set. So you can see our model is slowly improving, and we have a long way to go with just 1 epoch. So what I'll leave this for you as an exercise. I want you to actually train this for different amount of epochs. Train it, maybe even change up some parameters here. Just start playing with this. It's quite fun. You can start playing with learning rates as well. You can change the decay. Decay is basically how much the learning rate decreases. I'll explain these concepts later on in other slides. But for now, just know that we have a variety of things we can tweak. And deep learning is basically, people say it's an art form, and it kind of is, because there's so many variations that are dependent on each other. You can simply change some layers here, number of layers, change kernel sizes, change this, and there's no hard science that defines what to do to get the best results, mainly because it all depends on your data set. And your data set is basically naturally occurring images, which have so much naturally occurring variety in them. So once you kind of understand your data, you can start figuring out how you should tweak these parameters. And I'll discuss these things later on in other slides as we build more and more complicated classifiers. So I've left a code for you to plot your charts here, and you can run some tests as well. So for now, I'm going to just stop this quickly. And what I'm going to do is I'm going to just load, hopefully all the imports I needed are here. Load a model I trained before, and let's see if it works. No, it did not work because xtest isn't defined, so what we can do is just quickly run this block here, because xtest and xtrain and all those things are here. And we can run this, and this brings up this window. Here it is. So clearly this isn't a frog, this is probably a bird. And then we can just try it. This is not a dog, this is a dog, this is a horse, not a cat, this is a frog, yes, automobile, yes, bird, yes, automobile, not a frog, an airplane, yeah. So we can see, based on this as 10 samples, this model I trained here before, which I probably trained maybe just for 10 epochs, has about 50% accuracy. So let's see if we can beat that. Accuracy on Sapphire has reached very, very high, like 99%. Let's see if you can get to that on your own. Good luck. Hi, and welcome back to Chapter 10, where we introduced the concept of data augmentation. And the whole reason for data augmentation, which you'll learn soon, is how we can now use small data sets instead of super large data sets to train CNNs. So let's take a look at the contents of this chapter. Firstly, we take a look at how we split data into tests and training data sets. I'm going to give you a practical example where we start building a cats versus dogs classifier. However, previously we used Keras to basically load our data set into it. Now we're actually going to start downloading a data set of images and basically trying to create our own data set out of it and using it in Keras. Next, that's actually what we're going to do right at that point in 10.2, build a simple cats versus dogs classifier. And then we're going to boost the accuracy of this classifier using data augmentation. And then I'm going to discuss the different types of data augmentation that you will basically be able to use inside of Keras. Okay, so in this section we're actually going to learn how to actually bring images into our Python notebook and basically split them up into a test and training data set. And by doing this, we're actually going to start making a simple cats versus dogs classifier. So let's begin. Now firstly, if you're using Udemy, you can actually see there's a resources tied to this chapter. The title name of this file is cats vs dogs dataset. Download that file in your Ubuntu virtual machine, and I'll show you where to place this file once we go back to our Ubuntu screen, and from there you'll be good to go. Okay, so previously when we imported our datasets, we used Keras directly, and that was super easy to use. We just used Keras import mnist or cifar. However, now we actually want to build or basically create our own data set from some images. So assume you downloaded the cats vs dogs dataset, and if you use Mozilla and you logged into your Udemy, it's going to be in your downloads folder here. Alright, so this is a file I want you to extract. So double click on this file and extract it to go to our home or deep learning CV, which is our home directory name, and let's put the extracted file into our deep learning folder, and let's place this file into our data augmentation directory here. Alright, and I already have this folder named datasets here. However, I want you to actually create a new folder here. So before we do this, let's go to our file manager here, go to our deep learning CV, just so you know how to make folders in Ubuntu, and let me delete this since I already have it here. I'll delete that and I'll create a new folder called datasets, and this is where I want you to place that file that we extracted. So go back to our archive manager here and let's reload this, highlight datasets and press extract, and extraction completed successfully. Show those files. So now you can see you have datasets, you have a directory called images, and in this directory you just have a few thousand images. If you right click and press properties, actually you can see it right here, it's 3000 images selected here. Alright, so I probably shouldn't have done that right clicking thing there. Anyway, here we go. So it's back here. So what we need to do now, you can see, how do we actually get these files here into a training data set with X train, Y train, Y labels, test labels, all of those things, X test, Y label. So let's go to our notebook here. This is a notebook we're going to load up here. So go back to Mozilla. I already have it open here. So this is the path to the data set we just extracted. This is our raw data images. They're not in any order. Images are labeled like this, cat XXX being number, dog XXX being number as well. They're all JPEGs and they're all different sizes, by the way. They're not one square uniform size. So what we do, this is some simple code I wrote here, that basically this just gets all the files in that directory and stores them in a file name. And then we print the length just to make sure we get all our images. So that's 3000 images. So now we need to extract the labels. So as you can see, the structure we had before was files are cat or dog. If you scroll along to the bottom, you'll see dog. So we need to actually now store those cat and dog names as class labels. So go back to our IPython notebook. I would want you all to read this carefully, okay? So I'll go through it with you first. So we need to store the labels into ytrain and ythes. Those are the label files. Then we need to resize our images to 150 by 150. That's the standard dimension we're going to use for this test experiment. You can use any size you want. That's just the size I chose. And we're going to use 1,000 images of dogs and 1,000 images of cats as our training data. And then for our validation test data set, we're going to use 500 of each class. So you see this adds up to 3,000. 1,000, 1,000, 500 plus 500. And dogs will be labeled 1, cats 0. And then we're going to put all these files here into this directory structure. So it's going to be datasets, cats vs dogs, which is the name of our dataset here, and train. We're going to have a folder called train with all the dog images and one called train with all the cat images. This will be 1,000 dog images and 1,000 cat images. And then we're going to put 500 dogs and 500 cats in a folder called validation here. So let's see how this works. Now, since this isn't a Python course, I'm not going to actually explain this code to you in any super detail. However, you can intuitively just see what's happening here, and I'll try to explain it quickly. So what we're doing, we just have some parameters where we define the training size, the test size. We create some empty arrays, we define our size. We have some counts, and we make some directories here. So this is the directory names that I mentioned above. And we use this function to create the directories here. This get zeros thing is just to get the numbers correctly. Now this part is a bit tricky. It's probably not the best or most efficient code I've ever written, but it just basically what it does, it just goes through all those images, the dog images, pulls out the first 1,000, puts them in a training folder, then looks for the ones that are 1,000 to 1,500 in the dogs, puts them in the dog validation folder, and renames them and stores them correctly using OpenCV. And it does that for cats and dogs, giving them the correct label here. And once it's done, it stops this loop and says training and test data extraction complete. So let's run this code. It may take a little while, but let me just run this line here first. This should take about 20 to 30 seconds to run. When it's running, you see an asterisk here. I'm sure you're familiar with this by now. So I'll just wait here for it to finish. There we go, so it's done. So now what we're going to do, we're going to basically first let's look and see if this actually did what we said it would do. So we have our data sets here, that's where we saved the file. Good, we have our cats vs dogs folder, we have the train validation folders which we wanted, we have cats vs dogs in each directory, let's make sure. Now let's see if we have the images now, okay, that's the important part. Great, so we have the images here. We're supposed to have 1,000 cat images in this directory, and we should. It looks like about it. I'm not going to highlight it and do that thing again. Slow down my Explorer. But you can see here 1,000 images. If we highlight it here, dogs, 1,000 images as well. So let's just make sure. Excellent. And now go back to validation. Let's check those. Good. We have what looks like to be a lot less images. Should be 500, and it is 500. And likewise, we're going to have 500 dog images here. Now this is going to be the unseen test data that we're going to use to validate our model accuracy on. So we've created our data set here in this structure. We've resized our images. And now what do we do? So basically what we can do, we can actually, this is something I've done a lot. It actually, what it does, it uses NumPy saves feature to basically take the folders, take the training images here, and dump it into, because remember we have the images in arrays here. I don't know if you knew that. That's what I declared these empty arrays here. These lists or arrays store the images here. So what we're doing now, we're converting it to NumPy array and just storing it as an NPC file. So what this does, let's run it quickly. It creates these files here, and these files are basically the entire image data set in an NPC file. It's more like something like a zip file, but it stores our NumPy array. So let's go back to it. And this is a function here that I've written that actually acts exactly like the Keras data extraction stuff. So when you have mnist.load, sort of works exactly the same way. So this basically loads our training and test data and returns it into this form. So this is what we have done so far. So let's just make sure we can actually load our images that we've created from in our arrays. Sorry. So these are some random images that all have been resized to 150 by 150. That's why some of them may look a bit skewed. And there we go. So we've viewed some of our loaded images. Now let's get the images back in the form expected by Keras. So this is the function load data training and test that I've built that actually loads from our directory here. This specifies the directory name of our dataset and the file. Sorry, not the folder, but just the file name here. And what we do, we load it. Let's run this function. And there we go. So now we've reshaped our data exactly like how Keras wants it. So we have our training data being 2000 images, dimensions, and the depth, labels, test images, test labels. Perfect. So we're now ready to train a simple CNN to do some classification, well, to learn how to classify cats versus dogs. Okay, so now that we've loaded our data and brought it into the exact form that Keras needs to train on, we can now start building our dogs versus or cats versus dogs classifier. So let's begin. Okay, just some quick notes. So in the two previous CNNs we made, we use relatively small images, I can say tiny. MNIST was 28 by 28 and Sapphire was 32 by 32. Now we're using 150 by 150. So maybe you don't want to actually use that always when you're training a large image data sets because it's going to be quite slow. This one we'll find out how fast it trains, and we'll see, because now we have a lot less data. We have 2,000 images when previously we had 60,000 and 50,000. So let's see what happens. Okay, so we're back to our IPython notebook, and we're going to use a simple CNN similar to the one we use in our Sapphire classifier. Basically, there's only going to be two major differences though. Well, actually three. Firstly, it's going to be a different input shape and also a different batch size and epochs. I'm not going to really count that as a major difference because those are simple parameters we can always tweak for every model. Secondly though, the second major change is that we're no longer going to use a softmax final activation layer. We're going to use a sigmoid, and that's because it's a binary classifier. Binary meaning we're only two classes, yes, no, 0, 1 type classifier. And we're also going to use a different type of loss function called the binary cross entropy, as opposed to what we used before was a categorical cross entropy. And that one is used for multi-class classification problems, whereas binary is obviously used for two-class or binary class classification problems. So let's go ahead and create this model. I mean, the code is already run, but I can run it again. There we go. So it's a relatively simple model, as you saw, just about 1.2 million parameters. And now we're about to train our model. Okay, so basically I have a model.save. It's a good habit to always save your model here, and I'm not going to run this while you watch because that's going to be tedious to watch. I've ran this before I opened this notebook, and I have the results for you here. So basically, only with using 1,000 images, we're able to get some decent accuracy out of this. Let's see how good it performed. So I ran this for 25 epochs because it just takes about a minute to run an epoch. And basically the best accuracy we got, as you can see though, something important to note, our final accuracy and loss was 71%, 1.71 here. But if you take a look, 25 epochs, you can actually see sometimes the accuracy was higher. It actually peaked at around here, 73.6%. So technically, we had actually 73.7%, or actually 74.6% here. 0.74% here after a few epochs. So what that means though is that basically it stopped converging, it stopped improving results. Basically it was just feeding back into the stuff and it wasn't getting much better. So that is our peak accuracy we got there. So we save our model. So we can actually reload our model now. This is the model I just trained, hopefully. No, it's not. Let's actually get this model here. And let's see how it performs. Yep, got it right. It's a dog. That's actually a dog, not a cat. Cat, 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 dog, 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 dog. So it's actually pretty good. Got like 8 or 9 out of 10 correct there. So our results are pretty good, but could they be better? And yes, they can be better. And now we're going to introduce the concept of data augmentation, because this solves the problem of using less images. Because remember, deep learning, basically everyone says deep learning needs thousands of images, and I'm going to show you how you don't need thousands of images. We just simply need 1,000 images at least for each class, and we can create a pretty good classifier out of it. Hi, and welcome back to chapter 10.3, where we're actually going to learn how to boost accuracy with data augmentation. So let's first talk a bit about data augmentation. In the previous two CNNs, where we trained with simple classifiers, we had thousands and thousands of images per category. However, in deep learning, the more examples we have, usually the better our model. But what if we only had 1,000 examples per class? Let's see what happens here. So this is what data augmentation actually is. If we had 1,000 images, but we didn't have that much variation in the image, we can use Keras's data manipulation to basically generate all different types of versions of this image. Here you can see there's sharing, skewing, rotation, zooming, shifting left and right, and you can see it doesn't leave a black space in these images where it's got empty. It actually does something where it kind of fills in the last color here, and I'll talk about that soon. So this is how Keras actually creates data manipulation. So we have one simple image, and now we get 36 images out of it. So it helps basically not have our classifier overfit to the original data set, because especially when we have less data, overfitting becomes quite common because there's less variety in the data set. So the benefits of data augmentation is that it takes a small data set and makes it much larger. It's very easy to use, requires much less effort in creating a data set too, and I'll tell you why after. It adds tons of variations to the images that we just saw, and it reduces overfitting by increasing the variety in our training data set. So this is how we use Keras's data augmentation API. It's a just-in-time augmented data set. So what that means though is that it doesn't actually take 1,000 images and make 36,000 images, however how much different augmentations we want. What it does is that during each batch process, it does the manipulation in real time, so that even though it's finished an epoch, the first epoch basically will never be the same as the last epoch, even though it's the same data set, because each image is probably randomly, it's not probably, it is randomly manipulated to generate the manipulations we just saw here. So let's see how we use this. So basically it's quite simple. You'll see it in the code, but this is the essential parts of it here. So we create our image generator here, and we specify the types of augmentations we want. Rescaling is basically the normalizing we did before, where we bring it between 0 and 1. Sharing is basically sort of like twisting the image slightly. I'll show you an example soon. Zoom range is zooming in and out, so we have some of the data that's lost because it's zoomed in and cropped. And we have horizontal flips, and for the test data set, we just simply rescale here, because we don't want to manipulate the test data set. We want the test data set to remain as is. We just want to add the manipulations to the training data set. So this is the second part here. This is the actual generator now. This is where we actually pull the images, and the generator returns the images during training. This was just specifying how we wanted our manipulations to be. So we take what we defined here, which is our train data gen and our test data gen, and we basically tell it to take images from a directory. This is one way you can do it, but I actually find it's the best way. And we specify the folder. This can be the path to the images here. So in our case, it was datasets / cats vs dogs / train. And it automatically finds the classes there. We know it's a binary class because it's two classes, but we still have to specify it here. And we basically tell it the target size, which is 150 by 150, which we defined outside of this here, and the batch size. And we do the same for the test data gen here as well. So you can basically read what this flow from directory function does. It takes our image data and creates an iterator, which is a memory efficient method of returning a sequence of data. There's also a flow when we actually have the files differently. So lastly, this is how we actually fit the model now. Instead of actually using the test data and training data and all those things, it's a bit different now when we're doing model fit generator. We specify our train data generator, our train generator I should say. This is where we get our images from, here. Alright. Actually this is named wrong. This should actually be named train data generator, not test data generator. That's my bad. Back to this here, we define steps per epoch. Now, this is different to what you think. This is a number of training samples here, which would be 1,000 divided by the batch size. Okay, that's our steps per epoch parameter, and it's the same for the validation steps here. Don't overthink this. This is just a particular way our generators actually work, and that's it. We can start training our data set with our data augmentation. Hi, and welcome to chapter 10.4. It's a brief chapter where I talk about the different types of data augmentation that Keras offers. So let's quickly look at it here. So if you go to this link here, you can actually see the number of types of augmentation abilities that Keras has. In practice, the ones I found most useful are just these here. After, we'll go to that link and check out all. But for now, I wanted to explain what sharing was, because a lot of people do ask me what sharing is. Basically, it's a type of distortion where we sort of like manipulate the image perspective that we're looking at it. So imagine this is a square that was here, and after some X sharing, it actually looks slanted like this. That's what sharing does. And fill mode nearest, which I explained in the last slide, basically we can have constant, nearest, reflect, or wrap. That's basically how it looks differently. It's always good to use nearest. However, you can definitely experiment with these again and see. Depending on your data set, if it's like real world images, I would probably always use nearest. However, if it's certain things like numbers or whatever, you may want to try something different, like constant may actually be better for digits and characters. Alright? And what's good to know is that nearest doesn't really add new features. It isn't going to confuse the classifier too much. Okay, so what I'm going to do quickly now is go back to our IPython notebook, and I'm going to show you how to create many different manipulations randomly of an image, just for fun. You're not actually going to use this much unless you want to actually see and visualize how your manipulations are taking place. And before we even do that though, let's actually go back to Keras' site and we can take a look. It's already up here. All of the different augmentation techniques. You have different types of pre-processing and normalization. You have different types of like ZCA and PCA, those type of things that do like feature extraction, and ZCA whitening is quite commonly used, or at least used to be quite commonly used in computer vision. I don't think with deep learning it's used that much anymore, but Keras still offers it, which is nice. We have brightness, we have zooming, channel shifting, different fill modes I mentioned, vertical flips, rescaling, which is what we did before. So it's actually quite useful, and you can actually see some example code here on how to actually use some of these things. Okay, so now let's go back to our IPython notebook. All right, and we're actually going to see this is, where is it? Here. Let's open it here, and let's actually go to data augmentation here, and let's open up this demo slide here, this demo notebook. So what this does here, just basically shows you, let's load this data set. That happens the first time you run something with matplotlib sometimes. It doesn't actually show the graph. Alright, so now we see some random digits here. This is with no manipulations right now, an untouched data set. Now, how about we do some random rotations? Okay. Oh, I'm not going to, actually I can run it. It doesn't take that long to run. So here we see some random rotations. You can see some of these here in the middle actually don't look rotated at all. The 2 and 7 definitely are rotated. What about random sharing and zooming? Zooming, definitely you can tell this is zoomed, this is zoomed. This looks slightly zoomed if I'm not mistaken. Sharing isn't as obvious to see, but definitely I think this 4 is shared slightly, or this 9 is shared slightly. This 4 looks shared, definitely too. But you can see how sharing can take one person's handwritten digit and turn it into maybe someone else's one. So you're creating more data from existing data. What about horizontal and vertical flips? Got no idea what this is, so you actually should not do horizontal or vertical flips on digits. Digits are generally going to always be standardly written unless someone is doing something very weird. I'm not sure why they would do that. So that's fine. We can do some random shifts as well. You can definitely see this 1 and this 5. Actually, all of them have been shifted because they're usually centered in the middle. None of them seem centered right now. And you can apply all at once to get some very random distortions here, which is pretty cool. So you can take a look at my code to see how it's done. And now this is what I wanted to show you. Remember the dog image I mentioned here? Let's bring it up. Let's see how, if we run this combination of images here, and we do this 36 times, what's going to happen? So let's run this, and it saves in a folder called output directory. So let's go to the output directory here. Nice. So now we see we have 36 images. It actually looks like more. Maybe it did not write over my previous images, but now we can see exactly how our image manipulations, what they do to this poor dog. He is flying all over the place, which is quite cool. So you can see how we have one image that has become many, and we can actually play with these parameters here and keep generating more and more types of combinations. So basically this is a nice way to visualize exactly what our image data generator is doing.